What if one of the most mysterious places in the solar system was also one of the smallest and calmest? Welcome to the Sleepy Scientist. It is wonderful to have you here tonight, settling in for a quiet drift through the cosmos. These videos are made to be soft companions at the end of the day. Something gentle to rest your thoughts on as the world around you slows down. Tonight, we're travelling to Ceres, the quiet queen of the asteroid belt, a tiny world wrapped in ice, minerals and whispers from the earliest years of the solar system. Before we begin our journey outward, may I ask where you're watching from this evening? A bedroom with dim lights, a cosy sofa after a long day, somewhere halfway across the planet where the night has only just begun. And while you are here, if you enjoy these peaceful explorations and would like more sleepy science to drift off to, a like and a subscribe would mean so much. To those of you already subscribed, thank you sincerely for being part of this calm little corner of the internet. And if you would like to tap the notification bell as well, it will quietly let you know when the next bedtime journey is ready. There is always a delicate balance with these videos. Hopefully not so interesting that they keep you wide awake, but if they do, at least you will drift off a little wiser than before. So as we move gently toward this dim, distant world, here is a thought to carry with you. How did a world so small end up hiding secrets large enough to change our understanding of the solar system? Imagine drifting back to a time before the planets had taken shape, when the sun itself was still young and wrapped in a wide, hazy cloak of gas and dust. Light filtered through this cloud in soft golden streams, warming the innermost regions and leaving the outer stretches cool and dim. Across this vast disk, tiny grains of mineral dust floated and tumbled, each one no larger than the width of a human hair. Closer to the sun, these grains were dry and warm, baked by the new star's heat. Farther out, where the light faded and the cold deepened, each grain carried a thin, delicate layer of ice. It clung to them like frost on a window pane, fragile and shimmering, turning the outer disk into a region rich in frozen material. In this gentle environment, the earliest building blocks of worlds began to form. Dust drifted toward dust, and when two grains touched, they clung together. Not through force, but through a faint electrostatic attraction, a soft pulling as subtle as a whisper. These tiny unions grew, creating clumps no larger than grains of sand. Sand-sized clumps grew into pebbles. Pebbles collected into stones. Each step was small, but every tiny joining mattered. Over thousands of years, these clusters grew into objects you could hold in your hand, if hands had existed then. The region where the small world that would one day become Ceres began its story was a kind of middle ground. It was colder than the birthplace of Earth or Mars, giving it more water ice to work with. Yet it was not as frigid or distant as the realm where the outer giants gathered their bulk. It was a zone rich in frost and minerals, a balanced mixture of the ingredients needed to form a world that was part rocky body and part icy relic. This delicate blend would define its entire future. As these icy and dusty clumps met one another, the collisions were slow and soft. Nothing like the dramatic impacts often imagined. In the early solar system, everything drifted at a patient pace. A collision between two bodies the size of a small boulder felt more like the gentle pressing of two drifting clouds than an impact. And so, the bodies grew steadily, gathering mass without breaking apart. Over vast stretches of time, these clusters reached sizes measured not in centimeters or meters, but in kilometers. They became planetesimals, ancient seeds of future worlds, drifting on quiet paths around the sun. Among these early objects, one began to grow larger than most of its neighbours. As it pulled in more icy fragments and dusty material, its gravity strengthened. With more mass came more warmth, not from the sun, but from the inside. The decay of radioactive elements trapped within its rock released heat, and that warmth softened the boundaries between its layers. Heavy minerals settled inward. Lighter, icy material drifted upward. Slowly, steadily, this object reshaped itself from a lumpy, irregular body into a rounded, balanced form. This transformation is known as reaching hydrostatic equilibrium, and it set this growing world apart from the many still rough asteroids nearby. Ceres became spherical while its neighbours remained jagged and angular. That roundness was a quiet achievement, the signature of a world that had enough internal warmth to sort itself gently from the inside. It never grew large enough to become a full planet, but it crossed a threshold that most objects in its region never reached. It became something unique, something in between. A small world with the heart of a planet and the environment of an asteroid. Even as Ceres settled into its rounded shape, its history remained written inside its minerals, waiting to be discovered billions of years later. Some of these minerals carry hints that Ceres may not have formed exactly where it now orbits. Certain clays and salts inside Ceres contain ammonia, a material that struggles to survive in warmer regions. Ammonia-rich minerals form far from the sun in colder, darker parts of the disk. This means that Ceres might have begun its life much farther out, in a region rich in frozen compounds, before slowly migrating inward to the space between Mars and Jupiter. If that is true, then Ceres is not merely a resident of the asteroid belt. It is a traveller, a visitor carrying the chemistry of distant regions with it. Its ice, its clays, and its salts could be remnants of a colder birthplace, preserved across billions upon billions of years. These chemical clues are like faint echoes of its early environment, hints of a story that began far from where it now drifts. Picture the early solar system shifting and changing as gas flowed outward and inward, tugging small bodies along with it. In this slow, sweeping current, Ceres may have drifted gradually toward its present orbit, not rushed or thrown, but gently guided by the changing tides of the protoplanetary disk. By the time the gas cleared and the solar system settled into its long-term layout, Ceres had found its home between Mars and Jupiter, bringing with it a mixture of rock and ice that did not quite match its surroundings. The formation of this small world was not a sudden event. It was a quiet, almost meditative process. A handful of icy grains became a small pebble. The pebble became a drifting stone. The stone grew into a mountain-sized object. And over unimaginable spans of time, the mountain-sized object became a spherical dwarf planet, shaped by gravity, warmth, and the delicate mixture of materials that surrounded it. As the solar system continued to evolve, many early bodies were broken apart in collisions or consumed by larger planets. But Ceres survived. It endured the restless shuffling of the early disk, maintained its internal structure, and preserved the chemistry of its birth. By the time the last of the surrounding gas disappeared, Ceres was already complete, its shape set, its layers formed, and its story etched into the materials that filled its interior. When we look at Ceres today, drifting quietly in the dim belt between Mars and Jupiter, we see the result of this long and gentle story. A world that grew not through violence, but through patience. A world that nearly became a planet but remained small enough to carry the signature of its early formation unchanged. Every fold of its surface, every grain of its regolith, every mineral deep inside its crust traces back to the same origin. A time when the solar system was young and soft, and worlds were built from frost, dust, and the faint warmth hidden in ancient stone. The birth of Ceres is the story of a quiet survivor, a small world shaped by ice and time, carrying memories of its beginnings across billions of years. A world that shows how something modest in size can still hold a vast history, waiting silently in the darkness for someone to look closely enough to understand it. Between Mars and Jupiter lies a place often imagined as a restless swarm of rocks, a churning maze where every direction holds danger. Films and artwork tend to show it as a dense band of tumbling boulders, each one narrowly missing the next, as if chaos were the natural state of this region. In truth, the asteroid belt is nothing like that. It is an enormous ring of space, wide enough that light itself seems to thin out as it crosses the distance. Instead of swirling clusters, there are long stretches of emptiness where nothing passes for years at a time. The vast majority of this belt is quiet, open, and deeply serene. The scale of it is almost difficult to imagine. This region spans hundreds of millions of kilometers from its inner edge to its outer boundary, forming a broad ring around the sun. If you were to travel through it yourself, you could drift for days without seeing anything larger than a pebble. Space between asteroids is so immense that the idea of dodging rocks becomes almost humorous. The belt is spacious, peaceful, and slow. It feels more like a vast desert with a few scattered stones than a crowded river of debris. This quietness did not happen by accident. The asteroid belt became what it is because one nearby giant shaped its destiny. Jupiter, with its immense mass, played a dominant role in this region from the beginning. The giant planet's gravity was strong enough to interfere with the formation of a single large world between Mars and itself. Instead of letting the scattered material merge into a growing planet, Jupiter tugged at it constantly, pulling it just enough to keep the pieces from settling together. Every time rocky and icy objects tried to gather into something larger, Jupiter's influence nudged them apart again. This repeated pulling created a delicate but disruptive pattern in the belt. Certain orbital distances were especially unstable. Objects that wandered into these regions found themselves repeatedly tugged by Jupiter's rhythm, guided into new paths that took them away from their previous orbits. Over long timescales, those regions gradually emptied, forming what are known as the Kirkwood Gaps. These gaps are like quiet lanes woven into the belt, places where very few asteroids remain because Jupiter's gravitational timing gently removed them over millions of years. The belt today carries these patterns like soft scars, wide regions full of emptiness, others with clusters of stable families of asteroids, all shaped by the subtle push and pull of the solar system's largest planet. Yet even in the most populated areas, the distances between objects remain enormous. Two neighbours in the belt may be separated by thousands of kilometres, drifting so far apart that they would never know the other existed. The idea of frequent collisions is mostly a myth. Collisions do happen, but rarely, and usually at speeds far lower than imagined. Many are more like slow crumplings or soft merging events, with dust clouds drifting outward like powder shaken into still air. The environment here is gentle in another way as well. The sunlight that reaches the belt is dimmer than the warm glow felt on Earth. It arrives softened, more like late evening light than the bright midday sun. The temperature reflects this distance, sitting low enough to keep ice stable beneath the surface of many asteroids. Without air, without wind, without sound, This region of space feels like a place held in permanent dusk. Shadows fall sharply, colours mute themselves, and surfaces glow with only the faintest reflection from the sun. If you could float here, you might feel a strange sense of loneliness, but not an uncomfortable one, more like the quiet found in a wide open field where stillness itself becomes part of the landscape. In all this tranquility, Ceres moves along its path, completing one slow orbit around the Sun over the course of nearly 5 Earth years. Its motion is steady and unhurried, a graceful drift through a region where nothing rushes. Ceres is the largest object in this belt, yet even it is dwarfed by the distance around it. Its neighbours are small, scattered far apart, and rarely do any come close enough to make even a remote approach. The dwarf planet travels in solitude, wrapped in a thin cloud of dust that follows it faintly. This dust, created by tiny impacts over long stretches of time, forms a subtle halo around Ceres. The particles are so fine and so widely spread that they are almost impossible to see, but they contribute to the soft glow that surrounds the world. Imagine drifting beside Ceres as it moves through this quiet realm. The sun is a small, distant lantern. The darkness has weight, but not heaviness. It is a gentle darkness, the kind that encourages deep breaths and lingering thoughts. The belt does not roar or churn, it barely whispers. Most of the time, the only motion comes from Ceres itself, and the small grains of dust slowly falling through its faint gravity. The calmness of this region makes Ceres easy to overlook. It does not flash with bright colours or erupt with dramatic storms, yet this very quietness holds something beautiful. It feels ancient, undisturbed by the turmoil that shaped other parts of the solar system. While the inner planets endured collisions, heat and violence, the asteroid belt remained a slow-moving witness, holding on to the leftovers of creation. Ceres is the queen of these leftovers, a world that formed early and then simply remained, untroubled, unhurried, drifting through a vast, dim kingdom. If the inner planets are the bustling cities of our solar system, full of movement and energy, the asteroid belt is the silent countryside. And in that countryside, Ceres stands like an old rounded hill, rising from a landscape of scattered stones. It does not demand attention. It simply exists, steady and patient, carrying the memory of a different time. There is something almost soothing about how empty and expansive this region is. The belt has seen billions of years pass in silence. Stars have drifted across the sky. Comets have passed through like slow visitors, and through it all Ceres has kept to its path, rotating gently, orbiting steadily, and wearing a soft coat of dust shaped by countless tiny encounters. If you look closely, you can imagine the belt's history unfolding like a slow painting. Jupiter carving its patterns, sunlight dimming toward the outer edge, small bodies drifting farther apart over time. And in the centre of this quiet motion, Ceres travelling like a solitary lantern in the dark, bringing with it the secrets of the early solar system. The asteroid belt is not a place of chaos. It is a place of patience, a place where light fades softly and objects drift for ages without interruption. And in that peaceful expanse, Ceres moves with all the calm of a world that has never needed to hurry. For a world as small and quiet as Ceres, the idea of it being a dwarf planet might seem surprising at first. It does not tower like the giants of the outer solar system, and it does not shine brightly like Venus or hold moons in a proud orbit like Earth or Mars. Yet Ceres carries a quiet distinction, earned not through size or dramatic presence, but through the gentle power of gravity acting over vast stretches of time. Its status as a dwarf planet comes from a process called hydrostatic equilibrium, a calm and steady reshaping that took place long before any eye could witness it. Hydrostatic equilibrium may sound like a complex phrase, but the idea behind it is simple. When a world grows large enough, its own gravity begins to pull evenly in every direction at once. Over time, this balanced inward pull smooths out bumps and ridges, guiding the world toward a rounded shape. The larger the object, the stronger the pull, and the more dramatically it smooths itself into a sphere. It is as if gravity has a quiet preference for roundness, a soft persistence that slowly presses a world into balance. Ceres reached this point early in the history of the solar system. As it grew, collecting ice and rock from the drifting material around it, its gravity strengthened. Eventually, the pull inward became strong enough to rearrange its shape. The process did not happen quickly. It unfolded over millions upon millions of years, during which the small world gradually softened and rounded itself. Ridges settled, peaks sank, material shifted inward. Bit by bit, Ceres became smooth and whole, not because of external forces, but because of its own quiet weight pulling it toward the center. Many of the objects near Ceres never reached this stage. Vesta, for example, is only slightly smaller than Ceres but remains irregular, shaped by ancient impacts that carve deep scars across its surface. Hygeia, another large member of the belt, sits on the boundary of roundness but still displays uneven contours. These bodies did not accumulate enough mass to smooth themselves completely. Their gravity was never quite strong enough to guide them into equilibrium. As a result, they look more like broken fragments, shaped by chance and collisions rather than by internal balance. Ceres stands apart from them. It is round not because it is large in any dramatic sense, but because it crossed the necessary threshold for gravity to take over. Its smoothness reveals something important about its internal structure. While Ceres is made of rock, it also contains a significant amount of water ice mixed into its composition. This combination gives it a lower density than fully rocky bodies like Vesta. Ice, especially when warmed even slightly, can flow over long periods, helping to ease irregularities and smooth the shape of a world. Ceres had just the right mixture of materials and just enough warmth inside to become round. That warmth came from the decay of radioactive elements buried within the young world. In its earliest days, Ceres contained small amounts of isotopes that released heat as they broke down. This gentle internal warmth softened the boundary between rock and ice inside the planet. It allowed heavy materials to sink and lighter materials to rise, forming layers within the dwarf planet that are still hinted at today. While this inner heat faded as the centuries passed, the restructuring it caused remained, leaving Ceres with a core, a mantle of mixed rock and ice, and a crust shaped by its long cooling process. This early internal heat also contributed to the rounding of Ceres. With the interior warm enough to allow materials to shift, gravity had the freedom to sculpt the world more effectively. Instead of staying locked in an irregular, jagged shape, Ceres evolved into something more balanced. The heavy inner material settled toward the center, and the outer layers relaxed into a spherical form. When the heat eventually faded, the shape it left behind stayed intact, preserved like a quiet memory of its early history. Dwarf planets as a group are defined not by size, but by this ability to round themselves through hydrostatic equilibrium. They are not failed planets or half-finished worlds. They are simply bodies that reached the threshold for roundness, but did not clear their orbits of other material. Their environment played just as important a role as their internal physics. Ceres could not grow larger because Jupiter's immense gravity stirred the region and prevented a single dominant world from forming. The belt became a place of fragments, leftovers, and partially grown seeds, while Ceres remained the only one large enough to become spherical. In this way, dwarf planets are shaped as much by their surroundings as by their own interiors. They are products of the conditions that existed during their childhoods. Ceres sits as a perfect example of this. It is the right size in the right place, with the right mixture of materials to become round, but not large enough to clear its orbit of neighbours. It is an incomplete world only in the sense that it did not grow into a full planet. Yet its roundness, its internal layers, and its preserved chemistry make it far more complex than the many irregular bodies that surround it. There is something almost poetic about the idea that Ceres became a dwarf planet through softness rather than force. It did not dominate its region or consume surrounding bodies in violent collisions. Instead, it grew quietly until its own gravity gently reshaped it. Hydrostatic equilibrium is a calm process, a gradual surrender to balance. It gives Ceres a smoothness that speaks of patience, of long ages spent settling into its own identity. When astronomers look at Ceres today, they see a world that carries the marks of this process clearly. Its silhouette is rounded, its internal density hints at thick layers of ice. Its geological features suggest a history of internal movement, even if only early in its formation. The world we see now is the result of billions of years of slow settling, cooling, and quiet shaping. Even the classification of dwarf planet adds to its gentle identity. Being a dwarf planet means holding traits of both small bodies and larger planets. Ceres is planetary in its roundness and layering, but asteroidal in its environment and in the company it keeps. It bridges two categories, existing comfortably in between. It shows that the solar system's history is not made only of giants and dramatic forces, but also of small, persistent worlds, shaped by the steady influence of gravity and the quiet warmth of ancient heat. If you think of Ceres moving along its orbit today, turning slowly as sunlight glances off its muted surface, you can almost picture the long history that shaped it. A tiny world growing steadily in a cold region rich with ice, a warm interior rearranging itself, gravity pulling inward with gentle persistence. The result is a dwarf planet, a rounded world with a calm and balanced shape, carrying the memory of its early heat and the traces of its icy origins. And so the title of dwarf planet is not about grandeur. It is about the subtle triumph of gravity over irregularity. It is about a world that found its shape through quiet internal processes, not through overwhelming mass. Ceres earned that title not by commanding its surroundings, but by listening to its own internal pull, letting gravity smooth it into the form that best reflects its nature. It is a soft victory, a patient one, and it makes Ceres one of the most intriguing small worlds in the solar system. If you could sink slowly beneath the surface of Ceres, drifting through its outer layers as gently as falling snow, you would find that this small world is far more structured than it appears from above. It may not have continents or oceans or towering mountains like the larger planets, but beneath its muted grey crust lies a quiet, orderly architecture. Ceres is layered, shaped by the same fundamental processes that organize the inner rocky planets, only colder, softer, and far more subtle. It is almost like a miniature cousin to Earth or Mars, formed from similar principles but sculpted under much gentler conditions. The outermost layer of Ceres is a crust that carries the marks of countless ages. It is a mixture of icy grains, dusty minerals, and tiny fragments from past impacts, all pressed together under their own weight. Some parts are firm and compacted, while others remain loose and powdery, shaped by the gentle rain of micrometeorites that have fallen over the span of billions of years. The crust is not made of solid rock in the way Earth's crust is. Instead, it is a blend of water ice and hydrated minerals that have absorbed water into their structure, along with light dust grains that drifted down from ancient collisions. This mixture gives Ceres a crust that is both fragile and resilient. Over long stretches of time, the water ice slowly shifts, not enough to be dramatic, but enough to soften the boundaries between older and newer material. Mineral grains settle, compact, and gradually bond with surrounding ice. This creates a surface that feels ancient and quiet, like a layer of frost that has been gently rearranged by time rather than weather. The presence of hydrated minerals also hints that liquid water once interacted with this crust, altering its chemistry and leaving behind the frozen fingerprints of that ancient contact. Below this crust lies one of the most intriguing parts of Ceres, a suspected brine layer. This layer is believed to sit between the crust and the deeper mantle, acting as a slushy, salty zone similar to partially melted ice beneath a frozen lake. The brine is not expected to be a vast ocean, but more a collection of interwoven pockets and channels of salty liquid or softened ice. These solutions could contain mixtures of sodium carbonate and other dissolved minerals, the same materials seen in the bright patches on the surface. Although this briny layer is far from the warmth and fluidity of Earth's oceans, it may still behave like a slow-moving liquid over geological timescales, shifting gradually in response to internal pressures. Scientists learned about these hidden layers not by drilling into Ceres, a task still far beyond our current abilities, but through careful measurements of gravity. When the Dawn spacecraft orbited Ceres, it detected subtle variations in speed caused by tiny differences in mass underneath the surface. These variations act like clues about what lies inside. A region with denser material such as rock pulls the spacecraft slightly more strongly. A region with lighter material such as ice or brine exerts a softer pull. By mapping these variations across Ceres, researchers created a kind of interior portrait, revealing that the dwarf planet is not uniform but differentiated into layers of different density. This gravity mapping suggests that beneath the briny layer lies a mantle composed mostly of hydrated rock. This rock is not dry or rigid. Instead, it contains water locked into its minerals, giving it a softer, more ductile nature. It may be more comparable to a solid that behaves like an extremely slow-moving clay than to a typical rocky mantle. Over billions of years, this hydrated mantle may have cooled and stiffened, but pockets of warmth could linger. These residual warm regions might provide the faintest internal heat, enough to keep small portions of brine mobile even today. The possibility of liquid pockets within Ceres is one of the most fascinating aspects of its interior. Though Ceres is small and has long since lost the strong internal heat of its early years, some pockets may remain warm enough to prevent complete freezing. These liquid zones might be small, far smaller than any ocean, but they could still allow brine to move cautiously through cracks or fractures in the mantle. When pressure builds or when the crust fractures, these pockets may push upward, carrying dissolved minerals toward the surface. This could be how the bright patches in Okator crater formed, as rising brines evaporated and left behind shimmering salt deposits. Such pockets of liquid would not be turbulent or flowing in any familiar sense. Instead, they would move more like slow, creeping shadows of water, advancing at glacial speeds. But even this faint movement is enough to shape the geological character of Ceres. Over millions of years, the rising and cooling of brine could rearrange minerals, create fractures, and perhaps even contribute to the formation of gentle mounds or dome-like features. In a world as cold and calm as Ceres, even the softest internal activity becomes meaningful. If you travel deeper still into the lowest regions of the mantle, the materials would gradually become denser and more stable. This part of Ceres may be a mixture of hydrated rock and heavier minerals that settled long ago. The temperatures here, although cold by the standards of Earth's interior, are warmer than the surface and may remain high enough to influence how ice and rock interact at these depths. This lower mantle shows hints of the world's early heat, leftover warmth from the decay of radioactive elements that once stirred the interior into motion. All of these layers, crust, brine, hydrated mantle, and deeper rock, form a quiet, hidden structure that tells the story of Ceres's past. They reveal a world that once held enough heat to separate itself into distinct regions, much like a miniature planet. They show that water has played a crucial role throughout its history, not only on the surface but deep inside, where ancient processes may still linger in slow motion, and they suggest that Ceres, though small, preserves a more complex interior than most objects in the asteroid belt. Thinking about these layers invites a deeper appreciation for how even the smallest worlds can be shaped by the same physical principles that govern the larger planets. Gravity pulls heavy material downward. Heat enables movement and change. Water softens boundaries. Ice forms protective shells. All of these processes occur on Ceres, merely at a gentler pace, softened by cold and shaped by time. This layered structure also hints at the dwarf planet's resilience. Despite billions of years drifting in a cold, quiet region of space, Ceres retains traces of its early dynamism. The crust still bears the marks of interactions with liquid water. The suspected brine layer points to ongoing or recent internal movement, and the mantle, with its hydrated minerals and varying densities, suggests a history far more intricate than one might expect from such a modest world. Drifting downward in imagination through Ceres's layers feels like exploring a small frozen labyrinth. Every step reveals another chapter of its past, preserved in minerals and ice that have barely changed since they formed. It is a world shaped not by rapid geological upheaval, but by slow, steady processes acting over immense time. A world whose architecture is delicate but deeply informative, like the preserved layers of ancient ice core samples on Earth, telling stories of past climates and ancient atmospheres. Ceres' interior is quiet, but its silence is meaningful. It contains the blueprint of a world that nearly became more than it is. A world that began with warmth and water and slowly settled into its present form. Each layer is a reminder of the slow passage of time, the gentle work of gravity, and the persistent influence of ice in shaping the bodies of our solar system. Even if future missions explore Ceres up close, sending landers or drills to study its composition directly, the basic picture will remain one of quiet complexity. A surface shaped by dusty frost and impact fragments. A briny layer that hints at mobility. A mantle of hydrated rock that holds the memory of early heat. Together, these elements form a peaceful, layered world drifting through the asteroid belt, carrying its secrets within, always calm, always steady, and always waiting for curious minds to look a little deeper. Among the many craters scattered across the soft grey surface of Ceres, one stands out with a quiet insistence. Okator crater stretches across the dwarf planet like an ancient bowl, broad and deep with walls carved by a long-ago impact. From a distance it appears much like any other crater on this muted world. But when sunlight grazes its interior and the shadows fall at just the right angle, a set of bright patches ignite within it, glowing far more intensely than anything around them. These luminous spots scattered across its basin floor are what first drew the world's attention to Ceres in a way nothing else had. As the Dawn spacecraft approached Ceres on its slow, spiraling trajectory, these bright areas came into view long before the surface details sharpened. Even when Dawn was still far away, the spots shone so powerfully that they appeared as crisp, white points against the darker surroundings. Observers on Earth saw the images and immediately leaned forward, puzzled. Why would a small, cold world that had slumbered for billions of years suddenly reveal something that gleamed like polished stone or freshly exposed ice? At first, the ideas were simple guesses. Some researchers wondered whether fresh water ice had been exposed by a recent impact. Ice reflecting sunlight could certainly create bright patches, especially if it had not yet darkened from space weathering. Others considered the possibility of salts left behind from evaporating water, or even the gentle remnants of cryovolcanic activity, where subsurface brines might seep upward and freeze. The crater itself showed signs of complexity, fractures, slumped walls, and a central pit that hinted at internal processes. But no one could say with certainty what those bright spots were made of until Dawn moved closer and gathered more detailed data. When the spacecraft finally reached a low enough orbit to inspect Okator crater with clarity, the mystery deepened before it resolved. The largest of the bright areas, later named Cerealia Facula, was incredibly reflective. Smaller patches, called Venalia Faculae, dotted the basin floor like scattered frost, each one glowing softly against the dark ground. Spectral measurements from Dawn's instruments then provided the breakthrough. These bright materials were not fresh ice, nor were they metallic or crystalline in the way early imagination suggested. They were composed primarily of sodium carbonates, mineral salts that form when salty water evaporates and leaves behind shimmering crusts. Sodium carbonate is not a common sight on rocky planets. On Earth, it appears in places where alkaline lakes dry up, leaving bright reflective deposits across the ground. On Ceres, the presence of these salts was even more revealing. It meant that liquid brine containing dissolved minerals must have risen from beneath the surface at some point in the planet's history. When that brine reached the cold vacuum of space, the water rapidly evaporated or sublimated, leaving the salts behind. Over time, these salts accumulated in layers, creating the brilliant features we see today. This discovery transformed the understanding of Ceres. It suggested that the dwarf planet is not entirely frozen or inactive, but instead capable of transporting material from its interior to its surface through slow geological processes. Imagine briny water seeping upward through cracks or fractures in the crust, carried by pressure or by the gradual cooling of the interior. When it emerges into the frigid environment of Okator crater, the water escapes into space almost instantly, leaving behind delicate saltwork arranged by nature. These deposits catch sunlight with surprising intensity, making them shine against the dull background like tiny cosmic beacons. The brightness of these patches is not static. Over time they appear to fade slightly, and some have changed subtly in shape or reflectivity since dawn captured its first images. This slow transformation hints that the processes feeding them may have persisted longer than expected. Even if the brine is no longer actively rising, the residues left behind continue to evolve as they interact with sunlight, micrometeorites, and the delicate vacuum of space. Their gradual fading is a reminder that the story they tell is still unfolding on geological timescales, long after the initial activity ceased. There is something deeply compelling about the way these bright spots behave. They are not the result of explosive geological drama or violent eruptions. They are quiet features shaped by slow processes, by brine rising carefully upward, by minerals settling gently onto the surface. Their glow is not dramatic but serene, like the reflection of moonlight on salt flats back on Earth. And yet, despite their gentle nature, they captured the world's imagination with surprising force. When the first close-up images were released, people from around the globe paused to speculate. Some wondered whether the bright patches might be artificial lights, or signs of life, or evidence of something entirely unknown. More grounded ideas followed, but the emotional reaction remained the same. These luminous areas felt like a signal, a sign that even the quietest places in the solar system can hold unexpected beauty. For a moment, the world focused on a small dwarf planet that had drifted in near obscurity for billions of years, and found itself enchanted by the shimmer of ancient salts. The fascination came not only from the brightness itself, but from the contrast between what people expected and what they saw. Ceres had long been imagined as a dark, unchanging world, a place of muted colours and slow aging. To see something glowing so vividly on its surface felt almost like a secret being revealed. It hinted at warmth, at chemistry, at movement. It whispered that this dwarf planet was not simply a relic of the past, but a body with ongoing stories written into its crust. Okator crater stands today as a symbol of Ceres's hidden complexity. The bowl itself is shaped by ancient impact, but the bright spots within it belong to a much younger chapter. Some estimates suggest that Cerealia facula may be only a few million years old, quite recent when compared to the crater's age. In the timescale of the solar system, this makes the bright spots almost youthful. Their presence suggests that Ceres's interior remained active long after many of its neighbours cooled entirely. Looking at these bright regions feels like witnessing a message left on the surface by the interior below. They are the meeting point of two very different worlds. The cold, still exterior, and the warmer, briny subsurface where minerals dissolve and water creeps slowly through fractures. The salt deposits are the evidence of that connection, traces of an ancient interaction between ice, heat, and rock. They are quiet proof that even small worlds can carry the echoes of internal processes. When Dawn finally completed its mission, it left behind a treasure of images and data that continue to reshape our understanding of Ceres. Among all the features captured, the bright spots remain the most iconic, the most easily recognized, and the most emotionally evocative. They remind us that surprising beauty can appear even in places long overlooked. They show that the solar system still holds secrets gentle enough to whisper, but bright enough to catch our attention across vast distances. If you imagine standing at the edge of Okator crater, looking across the basin as sunlight creeps over the rim, You might picture the bright saltwork glowing like early morning frost. The air would be still, the sky a deep black, the ground silent beneath your feet, and yet the light from those bright patches would feel almost alive, a soft reminder that Ceres has its own quiet history bubbling beneath its surface. In the end, the bright spots are more than mineral deposits. They're a reflection of the hidden activity within Ceres, a link between its ancient interior and its present surface. They illuminate not only the crater they fill, but the story of the dwarf planet itself. A story of slow processes, gentle chemistry, and quiet transformation across unimaginable time. On most worlds with volcanic features, the word volcano brings to mind fountains of molten rock, glowing lava rivers, and heat pouring up from deep within. But on colder bodies, far from the sun's warming influence, volcanoes can take a very different form. Instead of erupting molten rock, they release chilled slurries of water, mud, and brine. This phenomenon is known as cryovolcanism, and it creates landscapes shaped not by fire but by frost. Rather than fiery bursts, these eruptions unfold slowly, sometimes so gradually that the surface seems to swell instead of explode. It is a kind of volcanism that speaks in whispers, not roars. Ceres, small and quiet as it is, bears one of the most intriguing cryovolcanic features in the solar system. Rising alone from an otherwise smooth plain is a mountain called Ahuna Mons. At first glance, it looks out of place, as if someone gently placed a solitary peak on a world that had no business producing mountains at all. Its profile is steep yet smooth, reaching a height of roughly 4 kilometers, standing taller than most of the surrounding terrain by a remarkable amount. The slopes are bright and youthful, lacking the scars and erosion marks seen elsewhere on Ceres. It is a mountain that seems almost fresh, as if it formed long after most of the dwarf planet had settled into stillness. The shape of Ahuna Mons is unusual. It does not have the ragged, fractured outline of a volcanic cone made from molten rock. Instead, it resembles a rounded dome, with smooth flanks that curve gently upward to a central peak. Its sides are streaked with bright lines, likely created by landslides of icy material slipping down the slopes. These streaks give the mountain a soft, almost brushed appearance, like layers of fine powder that have been gently disturbed. Understanding how such a mountain formed requires stepping into the world beneath Ceres's crust. Deep below the surface, pockets of briny water may remain, trapped in regions where leftover warmth from radioactive decay still lingers faintly. Over time, that brine can migrate upward, slowly pushing through softer layers of ice and mineral. When enough of it accumulates, it can create pressure that lifts the overlying material, forming a rising dome. The process is not violent. It is more like a bubble of cold mud pressing upward through a layer of frozen sand. Eventually, the pressure becomes too great for the crust above to hold. The dome cracks, and the brine, mixed with slushy ice and mineral fragments, oozes out. As it reaches the surface, the water content escapes into space, leaving behind a mound of solid material. Over long spans of time, as the rising slows and the last of the brine cools, the feature hardens into a mountain. Ahuna Mons appears to have formed through such a process, gradually building itself upward until it stood alone on the landscape, its smooth slopes marking it as a product of cold volcanic activity rather than molten rock. This kind of cryovolcanism is not unique to Ceres, but Ahuna Mons is one of the clearest, most dramatic examples. Other icy bodies, such as Pluto, show features that may have formed through similar mechanisms. Pluto's right mons and Picard mons, for example, rise like giant icy shields, built from upwellings of cold slurries rather than lava. But even these impressive formations lack the solitary elegance of Ahuna mons. On Ceres, the mountain stands alone, not part of a chain, not one peak among many, but a single icy monument on a wide, otherwise unremarkable plain. Its isolation raises an interesting question. Why only one? If Ceres has, or once had, the internal conditions to support cryovolcanism, why is there not a cluster of icy volcanoes scattered across its surface? One possibility is that cryovolcanism on Ceres is extremely rare, requiring a precise combination of internal pressure, material composition, and crustal weakness. Another possibility is that older cryovolcanic features once existed but have softened or collapsed over time, leaving Ahuna mons as the most recent, most intact survivor of a long geological history. The youthfulness of Ahuna mons suggests that it formed relatively recently in geological terms. Some estimates place its age at less than a few 100 million years, making it strikingly young compared to the rest of Ceres' surface, which bears scars hundreds of times older. In a solar system that is over 4 billion years old, a few 100 million years is practically yesterday. The mountain's bright, unworn slopes support this idea. They show little sign of the micrometeorite pitting or weathering that affects older features. Instead, they gleam with the freshness of a surface that has not yet been worn down. If Ahuna mons did indeed form recently, it implies that Ceres retained internal heat far longer than previously thought. Even a small world like Ceres can hold warmth deep within, especially if it contains hydrous minerals and frozen water that act as insulators. Over time, pockets of warmth could persist, allowing brine to remain mobile enough to rise. The existence of a cryovolcanic mountain less than a few 100 million years old suggests that Ceres' interior may still be evolving, slowly and quietly. The idea of a cold volcano may sound unusual, but the physics behind it are straightforward. On Earth, molten rock erupts because the interior is hot. On Ceres, chilled brine erupts because the interior is cold but not frozen solid. The key ingredient is mobility. If water mixed with salts can move even slightly, it can carry material upward. When that mixture reaches the surface of a low-gravity world with a thin or non-existent atmosphere, it behaves differently than it does on Earth. The water portion escapes swiftly, leaving behind mineral deposits that build into a mound. Ahuna mons is a beautiful demonstration of these processes. Its solitary presence adds to its mystery, almost as if it is the final breath of geological activity on a world drifting through darkness. Its slopes curve gently, almost elegantly, displaying patterns created by slow landslides of icy debris. Its flanks shimmer slightly when sunlight touches them, hinting at fresher material and a relatively recent origin. Standing near its base in imagination, one might feel a sense of stillness that is different from the calm across the rest of Ceres. The mountain rises from a plain that stretches endlessly, with few features interrupting the horizon. Its height would dominate the landscape, casting a long shadow across the quiet ground. And yet, knowing that this peak was formed not by hot magma but by cold, creeping brine would add a peculiar gentleness to the scene. Ahuna mons also provides a link to other icy bodies throughout the solar system, reminding us that volcanism is not always a fiery affair. On Enceladus, geysers of water erupt into space. On Titan, Cryovolcanic features may shape parts of the surface. On Pluto, massive icy domes tower over deep plains. These worlds show that cold volcanism can create landscapes just as varied and fascinating as those formed by molten rock. Ceres simply offers one of the closest and clearest examples, a glimpse into a form of geology shaped by frost rather than flame. The story of Ahuna Mons is one of quiet persistence. It is the result of internal pressures building slowly, of brine rising patiently through layers of ice and mineral, of material solidifying over time into a mountain. Its youth speaks of recent movement. Its brightness speaks of fresh material. Its shape speaks of gradual formation. Together, these traits tell the story of a small world still capable of change, even after most of its neighbours have long since cooled into silence. And so, Ahuna Mons stands alone, a singular icy monument lifting itself gently toward the sky. It is a reminder that even the smallest, calmest worlds can surprise us. A reminder that beneath a quiet surface, hidden forces may be at work, shaping landscapes at a pace so slow that only the passage of immense time reveals their presence. In the soft cold of the asteroid belt, this lone mountain rises as evidence that Ceres, though subdued, still carries a pulse of geological life. The surface of Ceres looks quiet from afar, a muted sphere with gentle tones and little in the way of dramatic contrast. If you were to drift closer, the colours would resolve into a soft charcoal grey with hints of blue and faint patches of brownish dust. Nothing is sharply coloured here. Everything seems softened, as if someone had taken a pastel drawing and brushed over it with a fingertip. The sunlight that reaches Ceres is weak, about as bright as a cloudy day on Earth, and that faint illumination gives the terrain a hushed, almost velvety appearance. The reflectivity of Ceres is surprisingly low. Its surface absorbs much of the light that touches it, reflecting only a small fraction back into space. This muted tone comes from the combination of dark minerals, fine dust, and ice-rich grains that have been mixed together over billions of years. Some of the darkest areas are rich in carbon-bearing compounds, while others reveal traces of hydrated materials that hint at ancient contact with water. Together, these components create a world that looks subdued and ancient, like stone that has weathered under starlight instead of wind or rain. The ground itself is covered in a layer of fine regolith, tiny fragments of rock and ice shattered by billions of years of micro-impacts. Even when no large collisions occur, the constant rain of tiny particles shapes the landscape. Each grain that strikes the surface kicks up another grain, slowly chipping and grinding the material into powder. Over immense time, this process creates a surface texture that is soft and dusty, like a thin blanket of charcoal-coloured flour spread across the world. This blanket is not uniform. It gathers in some areas, thins in others, moves slowly in response to landslides or subtle shaking beneath the crust, and builds up around crater rims where impacts churn the ground. Ceres carries countless craters across its surface, each telling a story of something that once struck the world with enough force to leave a mark. These craters vary widely in shape and depth. Some are shallow bowls, softened by the passage of time. Their rims have slumped inward. Their interiors are filled with dust and ice particles that settled after the impact. Others show collapsed walls, where the mixture of ice and rock beneath the surface gave way slowly, creating terraces or uneven floors. A few craters even contain central pits, depressions formed when heat from an impact melted part of the interior and the weakened material subsided. These pits give certain craters a distinctive, almost sculpted appearance. Among the largest features on Ceres is Kirwan Crater, a vast depression stretching more than 280 kilometers across. Despite its size, it does not rise dramatically from the surface. Instead, it sits like a shallow basin, its edges worn down, its interior patterned with subtle ridges and flows. The muted topography suggests that Kirwan formed in the distant past, so long ago that the surface has had time to relax under the slow influence of icy materials shifting beneath. The crater's floor carries faint streaks and irregularities, remnants of ancient events long faded into quiet stillness. Landslides are another gentle feature that shape the landscape of Ceres. Because much of the crust contains ice mixed with dust and rock, the material can behave differently than typical stone. When the surface slopes become steep enough, or when small vibrations ripple through the crust, icy debris can slip downward in long, gradual slides. These landslides leave behind smooth, fan-shaped deposits that spread across crater floors or down mountain slopes. Some appear to have happened recently in geological terms, with crisp edges and minimal erosion. Others have softened into the background, blending with the surrounding terrain. The landslides on Ceres are not dramatic avalanches like those on Earth. They unfold slowly, sometimes in near silence, as the icy grains drift downward. A single landslide may take centuries or millennia to fully complete, reshaping the ground at a pace far too slow for any observer to notice. Yet their presence reveals something subtle about the interior. Ice within the crust supports movement, even if that movement is glacially slow. Material can shift, settle, and release in ways that give the surface a softness, a fluidity, that might not be expected on such a small and cold world. Temperature variations across Ceres also contribute to its changing appearance. While the world is cold overall, temperatures fluctuate with latitude, local topography, and the angle of sunlight. Some regions, especially those at higher latitudes or in areas that remain in permanent shadow, are frigid enough to preserve surface ice over long periods. Other areas warm slightly during the day, causing exposed ice to sublimate, turning directly from solid to gas, and disappear into space. This sublimation process slowly erodes icy patches, leaving behind darker mineral residues. It also contributes to the faint long-term dust layer that covers much of the surface. Ceres lacks an atmosphere thick enough to trap heat or moderate these temperature swings. As a result, the surface can cool dramatically when sunlight fades, creating conditions where frost may form temporarily before vanishing again. The balance between sublimation and deposition means that some areas experience cycles where ice retreats and returns repeatedly over long stretches of time. These cycles leave delicate traces, such as bright streaks or patches that appear slightly lighter than the surrounding terrain. The dark, porous ground absorbs heat efficiently during the day and releases it quickly at night. This creates microenvironments where certain features warm just enough to initiate slow internal processes. Over immense time, even these tiny fluctuations help shape the surface into the patterns observed today. Materials expand and contract subtly. Grains shift. Ice migrates slowly. The world changes not through sudden events, but through the quiet accumulation of countless minor adjustments. If you were to stand on Ceres, the landscape around you would feel still, almost contemplative. The horizon would be low, the sky an unchanging black, and the sun a distant white disk hanging low in the sky. Shadows would fall sharply, without any air to diffuse the light. The ground beneath your feet will feel powdery and fine, with small pebbles scattered across the surface. Depending on the location, you might see the walls of an ancient crater stretching upward, their edges softened by time, or a broad plain merging with the horizon, broken only by subtle ridges or bright mineral patches. The muted colours of Ceres would evoke a sense of antiquity. Without wind or rain to reshape the terrain, features remain preserved for astonishing lengths of time. A small pebble displaced millennia ago could still be sitting exactly where it landed, untouched by weather or erosion. Even the marks of old landslides remain visible long after they settle, preserved in the low gravity and the cold stability of the crust. Kirwan Crater, with its enormous span, would dominate much of the landscape if you approached its edge. The view downward would reveal a basin so wide that its opposite side might fade into the distance. The ground within the crater might seem slightly smoother, marked by soft undulations rather than sharp features. Its sheer scale would speak of an impact so ancient that nearly every trace of the event's violence has been softened by time. The sublimation of exposed ice also leaves behind patterns that resemble faint brush strokes across the terrain. In regions where ice lingers just below the surface, impacts or landslides can expose patches that glisten faintly in the dim light. These bright patches fade slowly, transforming from icy shine to dull mineral brown over long periods. Even the subtle warmth of sunlight on Ceres is enough to shape these features, gradually erasing the evidence of freshly exposed ice. All of these elements, the fine regolith, the diverse crater shapes, the ancient landslides, and the shifting ice, work together to create a surface that is quietly beautiful. It does not dazzle with vivid colours or towering cliffs. Instead, its beauty comes from its subtlety. It is a place where the passage of time is written softly, where every grain of dust carries the memory of an impact, a shift, or a quiet chemical change. Walking across Ceres in your imagination feels like strolling through a world preserved in slow motion. Each feature tells a story that spans millions or billions of years. Every crater, ridge, and patch of bright mineral hints at processes that unfold too gradually for any observer to witness directly. It is a landscape shaped by patience, a world where small collisions, slow adjustments, and gentle ice-driven movements are the primary sculptors. In this quiet realm between Mars and Jupiter, the surface of Ceres records a history unlike any other. It is ancient but not static, cold but not lifeless, muted but deeply expressive. The charcoal grey ground, softened by dust and ice, invites a slower way of looking, a lingering gaze that allows the mind to drift into the deep calm of a world that has been changing in silence for billions of years. If you could take a pinch of dust from the surface of Ceres, hold it gently between your fingers, and somehow keep it from drifting away into the vacuum, you would be holding a tiny sample of the dwarf planet's long chemical history. That unassuming mixture of minerals and ice would reveal far more than its muted colour suggests. It would tell stories of water, distant origins, ancient heat, and even the faint possibility of organic chemistry quietly unfolding in a world many consider too small to be interesting. Ceres speaks through its chemistry, and the message it carries is richer than almost anyone expected before the Dawn spacecraft arrived. One of the clearest clues about Ceres' past lies in its ammoniated clays. These are minerals that contain ammonia locked into their structure, mixed with water-rich materials. Ammonia is not something that forms easily close to the sun. It requires cold conditions to stay stable, conditions far colder than those found in the asteroid belt today. The presence of ammoniated clays on Ceres is therefore surprising. It suggests that the dwarf planet's ingredients were formed or altered in a region much farther from the Sun, where temperatures were low enough to preserve ammonia in solid form. This raises the intriguing possibility that Ceres originated in the outer solar system before migrating inward to its current home. If Ceres did not form where it now drifts, then it carries the chemical fingerprints of a colder environment with it. This idea strengthens the growing picture of Ceres as a traveller, shaped by processes typical of distant icy worlds, rather than those of inner rocky ones. The ammoniated clays alone would make this a fascinating possibility, but they are only one part of the dwarf planet's chemical complexity. Ceres is also rich in hydrated minerals that have been chemically altered by contact with liquid water. These are not simply minerals that happen to contain ice. They are materials that have undergone reactions requiring water in its liquid form, not frozen. The presence of hydrated minerals across the surface suggests that Ceres once held significant amounts of liquid water beneath its crust. That water interacted with rock, altering the mineral structures and leaving behind stable signatures that remain visible today. These hydrated minerals tell a story of long-term interaction. They are not the product of a brief event such as a single impact melting part of the surface. Instead, they imply that water persisted in Ceres' interior for extended periods, moving through the porous rock and carrying dissolved minerals with it. Over time, this movement transformed the chemistry of the planet's outer layers. Even if most of that liquid has long since frozen, the evidence of its presence is still visible in the mineral signatures scattered across the surface. Another important family of materials on Ceres is the carbonates, especially sodium carbonates. These bright minerals, famously concentrated in the regions of Okator crater, form in alkaline environments where water interacts with rock in specific ways. On Earth, carbonates often appear in evaporating lakes or areas where groundwater brings dissolved minerals to the surface. Their presence on Ceres suggests that the dwarf planet once had regions where liquid water and chemical reactions created alkaline solutions rich in dissolved salts. When those solutions eventually reached the surface and evaporated, they left behind bright, reflective patches of carbonate minerals that still shine today. Carbonates also reveal something deeper. They indicate that the water within Ceres was not simply frozen or inert. It was chemically active, capable of dissolving minerals, transporting them, and precipitating them into new forms. This process requires some degree of internal heat, likely generated by the decay of radioactive materials early in Ceres' history. Even after the heat faded, the chemical products of these reactions remained, preserved in the crust like snapshots of a time when the dwarf planet's interior was warmer and more dynamic. One of the most surprising discoveries from the Dawn mission came from the region around Asteroid crater. Here, the spacecraft detected signatures of organic compounds, carbon-containing molecules that are the building blocks of many chemical reactions related to life. These organics were not spread evenly across the surface, but appeared concentrated in localized patches. The detection of organic material on Ceres immediately captured attention, not because it implied life, but because it hinted at the complex chemical processes that shaped the dwarf planet's history. Organic molecules on Ceres could have several possible origins. One idea is delivery from space. Meteorites loaded with organic material frequently fall onto planets, moons, and asteroids. The outer solar system in particular is rich in carbon-based compounds. If Ceres originated farther from the Sun, or remained in contact with such materials early in its formation, it could have accumulated organics through countless impacts. Another possibility is synthesis within Ceres itself. If the dwarf planet once held pockets of warm water interacting with carbon-rich minerals, it could have produced organic molecules through natural chemical reactions. This type of synthesis does not require life, only the right combination of temperature, water, and raw materials. Over time, these reactions could have created complex molecules that were later exposed through fractures, impacts, or the slow rise of brine toward the surface. A third possibility involves hydrothermal processes. Although Ceres never became warm enough to sustain volcanic systems like those on Earth, it may have hosted localized regions where heat from radioactive decay interacted with water and rock. These small warm pockets could have created the ideal conditions for organic chemistry to unfold. Once formed, the molecules could have migrated upward or remained trapped in the crust until exposed by a later event. Regardless of their origin, the organics near Ernetet crater add depth to the picture of Ceres as a chemically rich world. They suggest that the dwarf planet is not simply a frozen remnant, but a place where meaningful chemistry once occurred. This chemistry connects Ceres to other bodies where water, minerals, and organic compounds coexist, such as Europa, Enceladus, and even certain objects in the Kuiper belt. In this sense, Ceres is part of a larger network of icy worlds with intriguing chemical histories. Thinking about these chemical clues invites comparisons to many distant icy bodies. The ammoniated clays resemble materials found on outer solar system moons. The carbonates resemble deposits formed in alkaline lakes on Earth, but also in environments shaped by subsurface oceans on icy satellites. The hydrated minerals resemble those on asteroids altered by water early in their history. The organics echo the complex chemistry seen in comets and certain Kuiper belt objects. Ceres, in a way, is a meeting point for all of these influences. The dwarf planet's chemistry suggests a world that once held water in various phases: solid, slushy, and perhaps even liquid. It suggests internal movement, warmth, and exchange. It suggests a planet that received materials from far beyond its current orbit, and it suggests that beneath its quiet exterior lies evidence of processes that once shaped its interior in profound ways. Walking across Ceres in your imagination, the surface may look muted and grey, but beneath each step lies a world rich with chemical stories. Every grain of dust, every fragment of mineral, every bright patch of carbonate carries a record of interactions between water, rock, and heat. These interactions may have been slow, unfolding over millions of years, but their results are visible everywhere on the dwarf planet. The chemistry of Ceres reveals a world that is not defined merely by its size or location, but by its history. It shows how water shaped minerals, how minerals shaped surface features, how brines rose and evaporated, how organics appeared in unexpected places, and how the dwarf planet may have formed in a colder, more distant region before finding its home in the asteroid belt. In the soft cold between Mars and Jupiter, Ceres carries within it a museum of frozen chemistry. A museum filled with ammoniated clays from distant beginnings, hydrated minerals from ancient water flows, bright carbonates left behind by evaporating brine, and organic compounds that whisper of complex pathways. These chemical traces allow us to read the planet's past, not through dramatic geology, but through the quiet language of molecules preserved in time. And so, the chemistry of Ceres is a gentle reminder that even the smallest worlds can hold vast histories, a reminder that water leaves its marks in subtle ways, and a reminder that, beneath a grey and silent exterior, a world may be telling a story far richer than anything seen at first glance. When the spacecraft called Dawn first left Earth, it was unlike most of the machines we send into space. Instead of roaring with fire or relying on brief, powerful bursts of fuel, Dawn was built to travel with a gentler touch. Its engines were ion thrusters, devices that produced a steady, whisper-soft push by accelerating charged particles out into space. Each ion engine created only a small amount of thrust, no more force than the weight of a sheet of paper resting in your hand. But it applied that force continuously. Over months and years, that gentle, uninterrupted push added up to something remarkable. Ion propulsion produces a faint blue glow, a soft light that makes the spacecraft look almost serene. It is not the bright flame of a rocket plume or the fiery trail of a launch vehicle. Instead, the glow comes from xenon atoms that have been ionized and expelled at tremendous speed. Each atom glows briefly as it leaves the thruster, creating a pale, ghostly blue at the engine's edge. If you could have watched Dawn cruising through deep space, you might have seen this tiny blue shimmer against the blackness, a sign of the quiet force that carried the spacecraft across the solar system. Dawn's journey to Ceres was not straightforward, because Ceres was not its first destination. Before drifting toward the dwarf planet, Dawn travelled to Vesta, the second largest body in the asteroid belt. Vesta is very different from Ceres. It is brighter, drier, and far more rugged, shaped by enormous impacts and ancient lava flows. Dawn spent over a year mapping Vesta's complex surface, creating detailed images of its deep basins and towering ridges. That first mission gave Dawn's team the chance to test its systems and confirm that ion propulsion could guide a spacecraft reliably across long distances and into stable orbits around small worlds. After completing its work at Vesta, Dawn gently detached itself from the asteroid's gravitational influence and resumed its long drift. The spacecraft did not sprint through space. It glided, gradually spiraling outward on a path shaped by the faint, persistent push of its ion engines. As it travelled, the sun grew slightly smaller, the asteroid belt grew quieter, and the world ahead, Ceres, began to take shape as a distant point of light. This long journey required patience. For years, Dawn's engines hummed softly, adjusting the spacecraft's path with delicate precision. No violent maneuvers were needed. The mission was designed around the strength of ion propulsion. Slow, controlled, continuous acceleration. The spacecraft followed a curving trajectory that allowed it to match Ceres's orbit gradually rather than approach it abruptly. As Dawn drew closer, the dwarf planet slowly transformed from a bright dot into a round, muted sphere. The first images Dawn sent back from this distance were grainy and indistinct, but they were filled with anticipation. Even in these early pictures, the bright spots inside Okator crater shone through, appearing as white speckles on a dark background. Scientists and space enthusiasts alike stared at the images, wondering what could cause something so reflective on such a dark and ancient world. Dawn's approach had not even begun in earnest, and already Ceres was offering mysteries. As the spacecraft inched closer, its instruments began to reveal more. The surface resolved into craters, plains, and scattered bright patches. The limb of the dwarf planet, that thin edge separating darkness from light, grew sharper. Dawn's slow descent towards Ceres was not like the quick insertions of traditional missions. Instead, Dawn eased itself into orbit with the same soft push it used to travel through space. It began a spiraling path downward, moving into higher orbits first, circling the dwarf planet in wide loops, before gradually stepping closer in controlled stages. This careful approach was essential because Dawn was designed to orbit not just one world but two. Traditional propulsion systems would have made such a mission nearly impossible, but ion engines allowed Dawn to change its orbit slowly and efficiently, enabling it to slip into and out of celestial neighborhoods with surprising grace. When the spacecraft finally reached its first stable orbit around Ceres, it continued to spiral inward over time, each new orbit closer and more detailed than the last. The initial mapping orbit was high above the surface, giving Dawn a broad view of the dwarf planet's shape and major features. From this vantage point, the spacecraft produced its first global maps of Ceres, capturing the planet's muted colors and its assortment of craters. Scientists used these early maps to plan future orbits, selecting regions of interest and refining the approach route. After the high orbit came progressively lower ones. Dawn descended to an intermediate altitude where its instruments could measure temperatures, detect mineral signatures, and map variations in gravity. Each orbit added detail, transforming Ceres from a distant mystery into a complex world with subtle layers and striking features. Dawn's careful design allowed the spacecraft to adjust its orbit gradually, without using large amounts of propellant. The ion engines performed gentle nudges, guiding the spacecraft like a feather drifting downward through calm air. The lowest mapping orbit brought Dawn to an altitude where it could capture intricate details of the surface. From there, the spacecraft observed the bright patches of Okator crater in stunning clarity, revealing their fine textures and surrounding fractures. It photographed the smooth slopes of Ahuna Mons, traced the patterns of ancient landslides, and detected slight temperature variations on the surface. Gravity measurements from this altitude helped scientists piece together the internal structure of Ceres, confirming that it is layered and not homogeneous. Throughout this process, Dawn moved with a steadiness that reflected the nature of the world it was studying. The mission was never hurried or dramatic. Every shift in orbit was calculated, controlled, and smooth. The spacecraft orbited Ceres in a silent ballet, circling again and again until the maps were complete, until the chemical signatures were clear, until the mysteries became more defined. There is something inherently calming about the way Dawn approached and studied Ceres. The spacecraft itself seemed to match the dwarf planet's personality, quiet, persistent, and patient. Its gentle blue glow echoed the faint light that reaches Ceres from the sun. Its spiraling trajectory mirrored the slow movements of bodies in the asteroid belt, whereas some missions are defined by high-speed maneuvers and rapid-fire data collection. Dawn was defined by softness. It glided into place as if it belonged there. It is also worth appreciating how remarkable the mission was from an engineering perspective. Dawn became the first spacecraft ever to orbit two extraterrestrial worlds, a milestone made possible only by the consistency of ion propulsion. Without its gentle engines, the spacecraft could not have left Vesta, reached Ceres, or performed the delicate descent that produced the detailed maps scientists rely on today. Ion propulsion, once considered experimental, proved itself capable of guiding a spacecraft across vast distances with elegance and efficiency. When Dawn finally settled into its final orbit around Ceres, the spacecraft entered a phase where it would remain indefinitely. Its fuel eventually depleted, but its trajectory is stable. It continues to circle the dwarf planet silently, becoming a permanent companion to the world it studied so carefully. Down below, Ceres turns slowly in the dim sunlight, its bright spots shining faintly, its ancient craters holding their secrets, its icy interior whispering of a time when water moved through its layers. Thinking about Dawn orbiting Ceres brings a sense of peaceful continuity, a quiet spacecraft circling a quiet world, both suspended in the gentle darkness of the asteroid belt. The mission's arrival at Ceres was not marked by noise or drama, but by a soft blue glow and a slow spiral inward. And to this day, that quiet motion continues, a reminder that exploration can be patient and delicate, revealing beauty not through force, but through steady curiosity and calm persistence. When Dawn settled into orbit around Ceres, it did not rush into close inspection. Instead, it began with a broad, gentle sweep, circling from high above the dwarf planet where the entire world fit comfortably within each frame. From this altitude, Ceres looks smooth and muted, a sphere painted in charcoal greys and soft browns. The spacecraft drifted around it again and again, watching how craters revealed themselves under different angles of sunlight. This first mapping orbit allowed Dawn to build a simple global portrait, not yet detailed, but enough to understand the basic layout of the surface and to choose where deeper exploration should begin. As Dawn spiraled slowly inward, it entered a second mapping orbit that brought it noticeably closer. From this middle distance, the images sharpened. Crater rims showed texture. Bright patches stood out more clearly. The surface no longer looked like a single tone, but displayed subtle variations, like the grain of a stone slowly brought into focus. This orbit was designed for visible light imaging, using cameras that worked much like a human eye, but with far greater stability and clarity. These images allowed researchers to see the fine outlines of Ceres's landscape, providing the first hints of unusual formations such as ridges, troughs, and mysterious depressions. With each descent, Dawn moved into a more intimate relationship with Ceres. The next orbit, lower still, unlocked views sharp enough to distinguish individual boulders and landslide patterns. At this altitude, the spacecraft's instruments began to work in concert. Visible light images captured surface details, while an infrared spectrometer measured the wavelengths of sunlight reflected from the ground. Infrared light reveals the chemical identity of minerals because different substances absorb and emit heat in distinct ways. When Dawn mapped Ceres using infrared signatures, it began to uncover the chemistry of the surface: hydrated minerals, carbonates, organic compounds, and icy grains hidden beneath layers of dust. Alongside these imaging instruments, Dawn carried a device capable of mapping gravity variations. At first, this may sound like an unusual tool for exploring a planet's surface, but by tracking subtle changes in Dawn's motion as it orbited Ceres, scientists could detect where the dwarf planet's internal mass was concentrated. Denser areas pulled the spacecraft slightly faster, while lighter areas let it glide more freely. These shifts were tiny, but over time they painted a picture of what lay beneath the crust. Gravity mapping allowed researchers to confirm that Ceres is layered internally, with a mixture of rock, ice, and brine distributed in complex patterns. Each new orbit added another layer of understanding. One revealed shape, one revealed composition, one revealed internal structure. Together, they formed a multi-dimensional portrait of a world that had been a distant point of light for more than 2 centuries before Dawn arrived. Thermal mapping was another important step in understanding Ceres's surface. Using infrared observations at different times of day, Dawn measured how quickly various regions warmed in sunlight and cooled in darkness. These measurements showed that some areas retained heat slightly longer than others, hinting at differences in material composition or grain size. Warm regions could indicate finer dust or exposed rock, while colder ones might suggest patches of ice hidden beneath thin soil. One of the most surprising results from thermal mapping came from Okator crater, where the bright salt deposits showed temperature behavior unlike the surrounding terrain. These bright patches warmed and cooled differently, confirming that they were made of materials distinct from the darker regolith. The thermal signatures added yet another clue to the mystery of the salts, complementing the chemical evidence from spectroscopy. Topographic mapping emerged as Dawn descended to its lowest orbits. By capturing the same region from slightly different angles and comparing the images, the spacecraft's team created detailed elevation models. These models showed ridges that twisted across crater floors, troughs that stretched for kilometers, and gentle rises where material had shifted or accumulated. Some patterns hinted at ancient tectonic activity. Others suggested long-term movement of icy materials. These slight variations in height and slope allowed researchers to reconstruct the geologic history of Ceres with far greater accuracy than before. One particularly interesting discovery was the presence of subtle troughs and fractures that crisscrossed the surface. These features are difficult to see from a distance because the overall terrain of Ceres is relatively smooth, but with high-resolution mapping they became clear. Long, shallow grooves carved by stresses within the crust. These grooves hinted that Ceres once experienced internal changes significant enough to stretch or compress its surface. As Dawn continued to orbit, the spacecraft collected thousands upon thousands of images. Each orbit overlapped with the next, allowing scientists to stitch together a complete global map of Ceres in unprecedented clarity. The stitching process involved aligning images taken at different times, angles, and lighting conditions. It required careful correction for the spacecraft's motion, the curvature of the planet, and even the slight distortions caused by the camera lens. When finished, the global mosaic revealed Ceres in stunning detail. Every crater, ridge, trough, and bright spot arranged into a seamless portrait. This map became the foundation for nearly every scientific question researchers asked about Ceres. It showed where the brightest materials were concentrated, how large the landslides were, how deep the basins extended, and how the crust had been shaped by impacts and internal processes. It also helped identify regions of unusual chemistry. The organic deposits near Onutet crater, for example, could only be properly understood within the context of the detailed terrain surrounding them. From the perspective of someone drifting above Ceres, following Dawn's orbital path in imagination, each descent would feel like adjusting the focus of a camera lens. At first, you would see a round blur textured only by light and shadow. Then, as the orbit tightened, crater rims would appear. Slopes and ridges would gain definition. The dark patches across the surface would no longer seem uniform but varied and textured. In the lowest orbit, the world beneath you would resolve into fine details. A ridge a few hundred meters high, a fracture slicing across a crater floor, a bright splash of salt glistening against grey dust. The sensation would be similar to gliding just above the surface of a quiet world, feeling your understanding sharpen with each pass. You would notice that the world is not truly smooth, even if it appears so from afar. Its features may be gentle, but they are plentiful. Its slopes may be muted, but they carry ancient stories. This is the advantage of slow, patient mapping. It allows the subtleties of a world to reveal themselves over time. Mapping the surface of Ceres was about more than creating a snapshot. It was about understanding how the dwarf planet evolved. Each crater offered clues about impacts that shaped the landscape. Each landslide told of icy material shifting under gravity. Each bright patch revealed chemical processes beneath the crust. Each thermal signature hinted at the ways surface materials respond to the sun's faint heat. Dawn's mapping orbits transformed Ceres from a distant curiosity into a world with a deep, textured history. By the time Dawn completed its mapping campaign, researchers had a far clearer sense of Ceres's character. The maps showed a world with a layered interior, an active chemical history, and a surface shaped by both internal and external forces. It was not a static relic, but a world that had changed over time in gentle, persistent ways. The global mosaic that Dawn produced remains one of the mission's most impressive achievements. It turned a faint speck of light into a detailed landscape, a world of craters and plains, bright spots and dark patches, history and possibility. And as the spacecraft drifted in its final orbit, its cameras silent, the maps it created continued to speak for Ceres, revealing the delicate complexity of a world that quietly waited in the asteroid belt for someone to look closely enough to understand it. There is a quiet question that lingers over Ceres, a question that grows more compelling the longer one studies its surface and interior. Did this small, muted world once hold a global ocean beneath its crust? And if so, how much of that ancient water still remains today, hidden in cold layers that shift so slowly they might as well be dreaming? The evidence, scattered across minerals, densities and surface features, suggests that water has shaped Ceres more deeply than almost any other ingredient. It shaped the crust, altered the chemistry, softened the terrain, and may still be influencing the dwarf planet's interior even now. The idea of a past ocean begins with the density and overall shape of Ceres. Its average density is far lower than that of a purely rocky body, indicating that a significant fraction of its interior is made of water in one form or another. The dwarf planet's rounded, smooth shape also reveals that its early interior was warm enough for materials to rearrange themselves. Rock sank, ice rose, layers formed. Such internal organization is difficult to achieve unless liquid water had once been present, acting as a medium through which minerals could move and settle. These clues point to an early period when Ceres was not simply a frozen relic, but a warm, partially melted world with vast reservoirs of liquid beneath its surface. Minerals on the surface add more pieces to the puzzle. Hydrated minerals, those that have chemically interacted with liquid water, appear across the dwarf planet in abundance. Their presence requires not just water, but water that persisted long enough to alter rock in deep, meaningful ways. Carbonates, especially the bright sodium carbonates around Okator crater, are further signs of water-rich processes. These minerals tend to form in environments where liquid water dissolves materials, carries them upward, and leaves them behind when it evaporates or freezes away. Together, these chemical traces form a quiet chorus, pointing toward a world once shaped by flowing, circulating water. The source of the original heat that kept this ancient ocean liquid likely came from radiogenic warming. Early in the solar system's history, radioactive isotopes were more abundant in the materials used to build worlds. As these isotopes decayed, they released heat. Even in small bodies like Ceres, this warmth was enough to melt internal ice and create pockets or layers of liquid water. Over millions of years, these pockets merged, forming a global ocean sandwiched between a rocky core and an icy crust. The thickness of this ocean may have varied over time, but for long stretches of the dwarf planet's early life, Ceres was warm inside, with water gently moving through its inner layers. As time passed, the radiogenic heat faded, the ocean cooled, ice thickened above and below it, pressing inward. Eventually, much of the liquid froze, trapping dissolved salts and minerals within the crust. But the freezing of an ocean is not always a uniform process. Some regions cool faster, some remain insulated, some pockets of liquid linger. On Earth, deep lakes can remain unfrozen even when the surface freezes solid. In the quiet interior of Ceres, similar pockets may still exist, preserved by layers of insulating ice and salts that lower the freezing point. Evidence for present-day brine comes from several observations. The bright deposits in Okator crater appear younger than the crater itself, indicating recent activity. These bright materials are rich in sodium carbonates and other salts, which are difficult to bring to the surface without some form of liquid transport. The most plausible explanation is that brine, a chilled mixture of water and dissolved minerals, percolated upward through fractures in the crust. As it reached the surface, the water sublimated into space, leaving behind the glittering saltwork we see today. This process suggests that at least some brine remained mobile deep within Ceres in geologically recent times. Gravity mapping adds another layer of support. By observing slight changes in Dawn's motion, scientists detected areas beneath the crust that are less dense than rock, but more flexible than solid ice. These anomalies hint at slushy, partially melted zones that could behave like extremely slow-moving liquid. Such regions would not be vast oceans, but they could represent reservoirs of brine trapped between layers of crust and mantle, shifting over long time scales. If these briny pockets still exist, they could explain several surface features that otherwise seem puzzling. Ahuna Mons, with its smooth slopes and youthful appearance, resembles a cryovolcanic dome created by the slow rise of subsurface brine. The bright deposits in Okator crater may be the surface expression of the same process. Landslides across the dwarf planet's surface may also indicate icy material, softened by internal moisture, moving gradually under gravity. The slow movements of these brines would shape the crust in subtle ways. They would create fractures, weaken certain regions, and allow for repeated resurfacing events that refresh local terrain. Although the dwarf planet is not geologically active in the dramatic sense, its interior may still be quietly evolving, driven by the lingering heat of ancient decay and the unusual chemistry of its frozen ocean. The possibility of a long-lost or partially preserved ocean on Ceres invites comparisons to other icy worlds. Europa, the bright moon of Jupiter, holds a deep subsurface ocean kept warm by tidal forces. Enceladus, the small moon of Saturn, erupts plumes of water from its south pole, evidence of a global ocean beneath its icy shell. These bodies are larger, warmer, and more active than Ceres, yet they share similar ingredients: ice, rock, heat, and chemical diversity. Ceres is quieter than these moons, and its potential ocean would have been much shallower. But the basic principle remains the same. Water interacting with rock can produce complex chemistry. Water moving beneath the crust can create geological features. Water freezing and thawing over time can shape the evolution of an entire world. If a subsurface ocean once existed on Ceres, what might it have been like? Imagine a dark, cold sea enclosed by layers of ice above and rocky material below. The water would have been briny, rich in dissolved minerals. Hydrothermal reactions might have occurred at the boundary between water and rock, altering the chemistry and producing materials that later rose toward the surface. Over time, as the interior cooled, the ocean would have gradually retreated, leaving behind pockets of brine trapped in fractures and porous rock. Those pockets may still be there, holding on to the last traces of an ancient world shaped by water. Their slow movement could explain the dwarf planet's bright spots and cryovolcanic features. They could also provide environments where complex chemistry unfolds, although nothing suggests that life exists or ever existed on Ceres. The significance lies instead in the possibility that even a small dwarf planet can host the ingredients for rich chemical processes. The question of an ancient ocean on Ceres is not only about water, but about the nature of worlds that lie between the rocky planets and the icy moons. Ceres is a transitional object, carrying traits of both categories. It is part asteroid, part icy world, part frozen remnant of the solar system's early days. Its water history connects it to distant moons, while its location in the asteroid belt ties it to the inner planets. It stands at the crossroads of many evolutionary paths. Contemplating the possibility of an ancient ocean brings a sense of quiet wonder. It invites us to imagine a small world that once held warmth and water beneath its crust, a world where minerals dissolved, where brine shifted, where chemical reactions unfolded in the dark. It suggests that water, even in modest amounts, can profoundly shape a planet's history. Today, the surface of Ceres is cold and silent, but beneath that stillness may lie the last, faint echoes of a long-lost sea. A sea that shaped its minerals, sculpted its crust, and left behind clues in the form of bright patches, hydrated materials and subtle shifts detected by a passing spacecraft. Imagining that ocean adds depth to the quiet world we see now, reminding us that even the calmest places can hold stories of movement, warmth, and transformation hidden within. Life, in all its varied forms, depends on a few essential ingredients. It needs water in some accessible form, useful chemistry with molecules that can react and assemble, and a source of energy to drive those reactions forward. When contemplating whether Ceres could ever have hosted life, even the simplest kind, it helps to begin with these gentle foundations, not because they tell us that life must be present, but because they show us where to look for possibility, however faint or remote. Habitability is a quiet question, and on a world as muted and ancient as Ceres, it invites slow, thoughtful consideration. Ceres does not shout with signs of warmth or activity the way some outer moons do. It has no great plumes bursting into space, no clear evidence of a global ocean beneath its shell, no powerful internal engines that churn and reshape the surface. And yet, it holds whispers of the essential conditions. Water, chemistry, and energy all appear in small but meaningful forms, enough to raise the question even if the answer remains shrouded in the deep cold beneath the crust. Water is the simplest place to begin. Ceres is rich in ice, and almost all evidence suggests that liquid water once moved within it, circulating through the interior during its warmer, younger days. Hydrated minerals across the surface reveal long-term contact between water and rock. Bright sodium carbonates hint at brine that rose from within to leave minerals on the surface, and some studies suggest that patches of briny liquid may still exist today, trapped beneath insulating layers of ice and salt. Water need not be abundant or warm to matter. Even small pockets of brine preserved in the cold could represent pathways for interesting chemistry. Chemistry itself is the second component. On Ceres, it arrives in a surprisingly rich assortment. Hydrated minerals form when water interact with rock. Carbonates form in alkaline environments, where liquid water dissolves minerals and then leaves them behind when it freezes or evaporates. Ammoniated clays speak of a colder origin, possibly from the outer solar system where ammonia could survive long enough to become incorporated into minerals. And most intriguingly, organic molecules appear near Ernotet crater, carbon-based compounds that can form the backbone of far more complex chemistry. These organics do not indicate life, but they do show that the dwarf planet contains the necessary building blocks. Energy is the final ingredient, and it is perhaps the quietest one on Ceres. Today, the dwarf planet is cold and sluggish. But in its early life, radiogenic heat from the decay of radioactive elements would have warmed the interior. This heat was gentle, but over millions of years it kept ice melted into liquid water and drove chemical reactions between water, rock, and dissolved minerals. Even as the heat faded, chemical gradients may have persisted. Differences in composition or temperature that could support slow reactions. On Earth, microbes in deep environments sometimes survive entirely on these chemical gradients, drawing energy from the simple interaction of dissolved minerals. If similar gradients existed on Ceres, they could have offered a faint but steady source of chemical energy. In thinking about life in environments like these, scientists often turn to extremorphal organisms on Earth, life that thrives in places once thought inhospitable. These organisms live in freezing brines beneath Antarctic ice, in deep lakes sealed off from the surface for millions of years, in salty ponds where little else can survive, and in the tiny spaces between mineral grains in deep rock. Some extremophils use chemical reactions alone for energy, such as breaking apart simple molecules or absorbing minerals carried by groundwater. These analogues show that life does not need sunlight, warmth, or rich ecosystems to persist. It can survive in pockets of liquid brine at temperatures far below freezing, as long as chemistry and energy remain available. If life ever appeared on Ceres, it would have needed to find such a niche, perhaps in a warm pocket of water deep within the early ocean, perhaps along the boundary where liquid water brushed against mineral-rich rock, perhaps in a brine layer slowly circulating beneath the crust, carrying dissolved salts and carbon compounds. For a time, conditions may have been more favourable than they are today. The interior of Ceres would have been warmer during its first few 100 million years, with more liquid water and more energetic chemical reactions. If habitability existed, it likely peaked then, when water flowed through the interior and dissolved minerals into complex mixtures. As the dwarf planet cooled, any potential habitats would have contracted, brine pockets would have shrunk, warm regions would have diminished, chemical reactions would have slowed, but cooling does not necessarily erase all possibility. On Earth, isolated microbial communities continue to survive in ancient rocks deep underground, living on the faintest trickle of chemical energy. On icy moons, subsurface oceans persist beneath layers of insulation. On Mars, briny liquids may occasionally form even in extreme cold. If Ceres retains pockets of brine, even if only small ones, then chemically rich environments might still exist in the present day, locked deep beneath the surface, evolving so slowly that change becomes almost imperceptible. Yet speculation must be paired with caution. The presence of organics does not imply biology. The presence of water does not imply habitability. The presence of energy does not imply use. Scientists treat the question of life on Ceres with gentle reserve, noting the interesting ingredients while acknowledging the uncertainty that surrounds them. Ceres is not Europa, with its clear ocean. It is not Enceladus, with jets of water spraying into space. It is a quieter world, one whose clues whisper rather than shout. Still, the possibility invites reflection. To imagine a world this small and this cold once hosting simple life, or even the conditions for it, adds depth to the way we think about habitable places. It widens the boundaries. It suggests that life does not need dramatic oceans or great heat. It might emerge in brines that seep through rock, in pockets warmed only slightly by ancient heat, in environments dark and calm. On Earth, the most promising analogues for such a habitat lie in deep glacial environments. Within the ice of Antarctica, isolated liquid veins form where pressure and impurities lower the freezing point. Microbes live within these veins, metabolizing slowly, sometimes dividing only once every few years. They survive on minimal energy, enduring conditions once thought too extreme for biology. Other analogues exist in deep subsurface brines, where organisms rely solely on the chemistry of surrounding rock. These environments hint at what might be possible in a place like Ceres, where water and minerals meet in cold, dark spaces. If simple life ever emerged on Ceres, it would not have thrived in the dramatic sense. It would have persisted quietly, its existence defined by patience. No blooms, no ecosystems, no large-scale movement, just the slow rhythm of survival, in a world where time moves at the pace of ice. And if such life once existed but no longer does, the chemical traces might remain, preserved in minerals or brine deposits. They would be subtle, requiring instruments far more sensitive than anything yet sent to Ceres. But the possibility remains, faint but meaningful. Contemplating whether Ceres could host life shifts the focus from certainty to curiosity. It invites us to imagine how many worlds might fit the narrow window of necessary conditions. Not worlds with dramatic oceans or thick atmospheres, but small bodies with just enough water, just enough chemistry, and just enough warmth to allow something simple to begin. Ceres shows that habitability is not a yes or no concept. It is a spectrum, with different worlds occupying different places along it. In the end, the question is not simply whether life exists or existed. It's about understanding the environments where life could emerge, even briefly. Ceres offers a valuable example of such a world, small, cold, and quiet, yet rich in water and chemistry. A world that might never have supported life, but could have come close. A world that teaches us how delicate, how sparse, and how surprising the conditions for habitability can be. And so the idea of life on Ceres remains a quiet contemplation, not a proclamation, not a certainty, but a gentle wondering, a recognition that even the smallest worlds may hold possibilities, that even the most muted landscapes may have once carried the ingredients of life in their hidden depths. It is a thought best approached slowly, with curiosity rather than expectation, letting the imagination drift through the still, cold brines beneath the crust, where chemistry once moved in a world now resting in silence. Ceres moves through the solar system with a calm, unhurried rhythm, turning slowly beneath the dim sunlight that filters through the asteroid belt. Its rotation is gentle, taking a little over 9 hours to complete a full spin, which makes its days short compared to Earth. Yet the light that fills each of these days is so faint and delicate that time feels stretched, almost as if the dwarf planet lives in a permanent state of early morning. Shadows fall sharply across the surface, and even at midday the sun looks more like a distant lantern than the warm disk familiar from home. The axis of Ceres tilts only slightly relative to its orbit. This mild inclination means that its seasons are subtle, far less pronounced than the dramatic shifts experienced on Earth or Mars. There are no sweltering summers or brittle winters. Instead, the dwarf planet experiences a long, steady cycle of gently shifting sunlight as it spleets each of its years, which last nearly 5 Earth years. These slow changes influence how much warmth reaches the surface, even though the difference between the warmest and coldest times of year remains small. For a world this distant from the sun, even a modest tilt can create a quiet rhythm of light and temperature. Sunlight itself is a rare resource on Ceres. Because the dwarf planet lies far from the sun, the light arriving at its surface is dimmer by a large margin. This lower light level shapes everything, from temperature cycles to the behavior of ice. In regions where the sun does shine, surfaces warm just enough to slightly change the chemistry of minerals or to initiate the slow sublimation of exposed ice. In shadowed areas, however, the cold persists without interruption, creating some of the chilliest environments anywhere in the inner solar system. The combination of weak light and slow seasonal change creates a world where time feels elongated and where even subtle movements of sunlight have outsized effects. The poles of Ceres are particularly interesting. Because of the dwarf planet's gentle axial tilt, sunlight never reaches deep into certain craters near the poles. These permanently shadowed regions remain cold enough to preserve ice for millions, potentially billions, of years. Within these polar cold traps, temperatures drop low enough that ice becomes stable indefinitely, even if just a thin layer rests at the surface. These craters act as natural freezers, holding ancient frost that has survived long after the surrounding landscape lost its water to sublimation. If you could descend into one of these shadowed basins, you would find yourself in a place that has not seen direct sunlight since the earliest days of the solar system. Beyond these deep shadows lie areas where sunlight glances across the landscape only briefly during Ceres's long year. These regions experience slow cycles of warming and cooling, where surface ice may retreat slightly during warmer periods and reaccumulate during colder ones. The changes unfold so gradually that each cycle blends into the next. Yet over time these patterns leave faint marks on the landscape, patches of brighter material, subtle frost layers, and minute differences in mineral composition. It is in these marginal zones, neither fully shadowed nor fully illuminated, that the interplay between sunlight and ice becomes most noticeable. Ceres' long orbit also influences how surface features evolve. During the dwarf planet's distant winter, sunlight becomes even fainter, allowing volatile materials like water ice and carbon dioxide frost to remain stable even at lower latitudes. As Ceres drifts back toward the slightly warmer parts of its orbit, these materials may begin to sublimate, rising from solid into thin, invisible vapors that drift across the surface. Although the dwarf planet lacks a true atmosphere, these brief vapor movements can redistribute material ever so slightly, depositing frost in cooler areas and leaving darker residue where the ice has vanished. Shadowed craters at the poles provide a window into this long-term cycling of frost. Their darkness shields their floors from sunlight entirely, creating reservoirs of ancient ice that escaped the warming periods experienced by the rest of the surface. These places act as time capsules, holding ice that may have arrived from within Ceres, from early impacts, or even from passing comets billions of years ago. Because the cold is so extreme within these traps, the ice remains pristine, barely altered since it first settled. Such deposits can tell scientists about the dwarf planet's earliest conditions and the kinds of materials that populated the inner solar system long ago. Other parts of the surface reveal how temperature cycles influence the behavior of minerals. Some carbonates, for instance, appear more stable in cooler environments, while hydrated minerals show signs of dehydration if exposed to warmer conditions for long enough. Over countless years, even the small seasonal variations of Ceres can encourage surface materials to reorganize themselves. These processes happen so slowly that they are invisible over human timescales, but the cumulative effects shape the chemistry and appearance of the dwarf planet's surface in profound ways. The interplay between sunlight and shadow also influences the faint dust that coats much of Ceres. In sunlit areas, the surface heats and cools with each short day, causing grains of dust to expand and contract in tiny cycles. This gentle breathing of the soil can loosen material, allowing it to shift downslope or to accumulate in sheltered hollows. In shadowed areas, dust remains locked in place, forming a stable blanket that may persist for ages. Over time, these subtle movements create patterns of light and dark that contribute to the dwarf planet's softly mottled appearance. Even the bright patches at Okator crater respond to Ceres' seasonal rhythm. Although they are made primarily of reflective salts, these materials undergo tiny changes as temperatures rise and fall. Some areas appear to have faded slightly since Dawn first photographed them, suggesting that sublimation or gradual chemical alteration continues to shape the deposits. The timing of these changes may be influenced by the dwarf planet's orbit, as warmer periods promote subtle reactions that colder ones suppress. If you were able to stand on the surface of Ceres and watch the sky, you would notice the sun tracing a slow, shallow arc. In many regions, the sun never climbs high overhead, instead hovering near the horizon for much of the day. Shadows would be long, stretching across crater floors and spilling over ridges. Because the light is so faint, the ground would glow softly rather than gleam. The passing of seasons would be gentle, marked not by dramatic weather, but by the slow drift of sunlight across the terrain. The length of a Cererian year means that change comes in extended phases. A single winter could last more than 2 Earth years, giving frost ample time to accumulate in shaded regions. A single summer could last just as long, allowing ice on exposed slopes to retreat grain by grain. The entire surface lives by this long rhythm, its chemistry responding gradually to the distant pull of the sun. Comparing Ceres to other worlds helps highlight how unique its seasonal rhythm is. Mars, with its significant tilt, experiences dramatic changes with dust storms and shifting ice caps. Earth's tilt brings familiar summer warmth and winter chill. Jupiter's moons often experience tidal heating that overwhelms any seasonal effects. But Ceres resides in a quieter category. Its seasons do not reshape the surface but gently influence it. Its poles harbour long-lasting shadows where ice can outlive continents. Its slow orbit and faint sunlight create a world where time stretches, and where each year feels like a patient unfolding of small, delicate changes. In this calm environment, temperature cycles become one of the dwarf planet's most important sculptors. They determine where ice survives, where it sublimates, where minerals shift, and where chemistry evolves. They help explain the distribution of bright patches, the subtle differences in surface texture, and the longevity of ancient frost. Ceres' orbit and seasons offer a peaceful window into a world that moves to a softer rhythm than our own. A rhythm shaped by distance, by cold, by a gentle tilt, and by a sun that warms just enough to stir a whisper of change but not enough to erase the quiet beauty of its ancient surface. In the earliest days of the solar system, long before the planets had found their places, countless small bodies drifted through the protoplanetary disk. They were the first solid objects to form, the seeds from which larger worlds would eventually grow. Some merged into planets, others shattered in collisions. A few, like Ceres, survived mostly intact, carrying within them the chemical and structural memories of that ancient time. Small worlds such as this one are essential to understanding planetary evolution, not because they became grand and complex, but because they stayed simple. They act as time capsules, holding evidence that larger planets erased through heat, erosion, and geological activity. Ceres is especially important in this story because it preserves the distribution of water from the early solar system in a way that larger worlds no longer can. Its ice-rich interior, its hydrated minerals, and its briny chemistry all point to a time when water was far more widely available than one might assume from the dry surfaces of the inner planets today. In its composition, Ceres record where water once accumulated, how far it extended toward the sun, and how it interacted with the rocky materials forming in that region. On Earth, water reshaped the surface multiple times. On Mars, ancient rivers left behind altered landscapes. But both worlds have active or once active geology that obscures their earliest histories. Ceres, by contrast, has preserved its water signature with remarkable clarity. The chemistry of Ceres also reflects a boundary region between the inner and outer solar system. The presence of ammoniated clays suggests that at least some of its material came from much colder regions, where ammonia could remain stable long enough to become incorporated into minerals. This is a clue that Ceres may have formed farther from the Sun than where it orbits today, or that its ingredients were mixed from different parts of the early disk. At the same time, Ceres contains minerals such as carbonates and hydrated rock that resemble those found on objects closer to the Sun. In this way, Ceres serves as a bridge, linking materials typical of the warm inner system with those of the icy outer system. This blend of characteristics makes Ceres a valuable point of comparison to dwarf planets in the Kuiper belt. Bodies like Pluto and Haumea formed in environments rich in volatile ices and low temperatures. Although Ceres is much smaller and now resides in the asteroid belt, its chemistry resembles these more distant icy worlds in striking ways. Both contain mixtures of rock, ice, and complex organics. Both show signs of past or present cryovolcanism. Both display surface features shaped by the movement of frozen materials rather than molten rock. These parallels suggest that the processes that formed dwarf planets in the outer reaches of the solar system may not be as different from those near the snowline as once believed. Ceres also offers insights into how the Sun's early environment influenced planetary formation. When the Sun was young, it emitted stronger radiation and experienced more frequent bursts of energetic particles. These early conditions affected how ices evaporated, how dust grains stuck together, and how chemical gradients formed across the protoplanetary disk. Ceres, with its mixture of volatile-rich and rock-rich materials, retains a record of these gradients. The distribution of water inside it, the types of salts on its surface, and the presence of ammonia in its minerals all tell scientists about the temperature and composition of the disk during the time of its formation. Some models propose that early turbulence in the disk scattered small icy bodies inward from the outer solar system, placing water-rich materials into regions where rocky worlds were forming. If this scattering occurred, Ceres may be a remnant of that process, a body that retained its original chemistry even after migrating to its current orbit. Studying Ceres helps researchers test these models, providing evidence for how the Sun's early radiation shaped the distribution of elements that later formed planets. The very structure of Ceres reveals something important about planetary evolution. Larger planets differentiate into cores, mantles, and crusts through intense heat and pressure. Smaller bodies often remain lumpy and irregular. Ceres, sitting between these categories, is partially differentiated. It has layers but not fully developed ones. It experienced internal heat but not enough to erase all signs of its early history. This middle ground structure helps scientists understand the threshold conditions required for a world to become spherical, to maintain internal oceans, or to sustain geological activity. Because Ceres did not grow large enough to clear its orbit or ignite sustained internal heating, it remains in a preserved state, neither fully evolved nor untouched. This makes it a perfect subject for studying planetary adolescence, the stage between initial formation and mature differentiation. It tells us how water shapes early interiors, how small bodies respond to radiogenic heat, and how chemistry evolves when a world hovers between being an asteroid and a planet. Even the surface of Ceres contributes to this larger story. Its craters show evidence of impacts throughout solar system history, from early heavy bombardment to more recent collisions. The distribution of bright salts and the signs of cryovolcanism reveal how brine interacted with the crust long after the original ocean began to freeze. These features help scientists reconstruct how volatile materials move through planetary crusts, shedding light on geological pathways that may have operated on early Earth and Mars as well. The organics found near Ernetet crater hint at the kinds of molecules that may have been widespread during the solar system's formation. Whether these organics formed on Ceres or arrived through impacts, their presence contributes to the understanding of how prebiotic chemistry may have been distributed across the solar system. They help address questions about how early Earth acquired its organic inventory, and whether similar processes occurred on other forming planets. Ceres also helps illuminate the broader question of planetary diversity. Why did some small bodies become icy worlds with subsurface oceans, while others remained dry and rocky? Why did some accumulate ammonia-rich compounds while others did not? The answers lie in the interplay between distance from the Sun, timing of formation, availability of heat, composition of the protoplanetary disk, and gravitational influences from the giant planets. Ceres sits at a crossroads where these factors intersect. Studying it sharpens the scientific understanding of how many different paths planetary formation can take. On a larger scale, Ceres reminds us that the solar system's first few million years were chaotic but creative. Dust grains grew into pebbles, pebbles into planetesimals, planetesimals into worlds. Some worlds survived largely unchanged. Others grew into planets with oceans, atmospheres, and surface reshaping. Ceres represents a branch of this evolutionary tree that did not grow tall but remained rooted in its early form. Its chemical signatures, layered interior, and icy past all preserve the environment from which it emerged. Reflecting on Ceres in this context gives a sense of how even a modest world can illuminate enormous questions. It holds clues to water distribution, to chemical pathways, to the mixing of materials from distant regions, and to the thermal histories of small bodies. It helps connect the rocky inner planets to the icy outer worlds, showing that the boundaries between them are not as sharp as once believed. And it offers a record of the solar system's youth, preserved in a sphere barely 1,000 kilometers wide. In this way, Ceres becomes not just a solitary dwarf planet drifting in the asteroid belt, but a key storyteller in the history of planetary evolution. A small, quiet world holding secrets of how planets grow, how chemistry spreads, and how the early sun shaped the places that would one day become home to moons, oceans, and eventually life. Dreaming forward into the future of Ceres, exploration feels a little like gazing into the quiet distance of the asteroid belt itself. The dwarf planet drifts there patiently, holding its secrets with the kind of calm persistence that makes scientists eager to return. The Dawn mission gave us extraordinary insight, but it also revealed how much remains unknown, and how many mysteries could be solved only by touching Ceres directly, studying its materials up close, or listening to the faint movements beneath its crust. The next chapters of exploration will require new spacecraft, new techniques, and new ways of approaching a world that moves at such a gentle pace. One of the most eagerly discussed ideas is a sample return mission. Bringing even a small amount of material from Ceres back to Earth would allow laboratories to perform detailed measurements that no spacecraft instrument could match. A pinch of its salty crust, a grain of dark regolith, a fragment of carbonate from a bright patch. Each would reveal layers of information about chemistry, temperature histories, and the interactions between water and rock over billions of years. Scientists imagine collecting samples near Okator crater, where brines once reached the surface, or from regions where organics cluster, or even from ancient frost preserved in polar shadow. Every location offers a different window into Ceres' past, but returning samples from such a distant, low-gravity world requires careful design. Engineers imagine landers that softly touch down using thrusters rather than relying on heavy structures, since gravity offers only the faintest assistance. A small sampling arm might sweep or drill, collecting grains and sealed cores before launching a tiny ascent module back into space. These technologies already exist in early forms, but tailoring them to Ceres' calm environment would require refining their precision and reducing their mass. The scientific reward, however, would be enormous. Direct access to water-altered minerals, organic compounds in their native setting, and isotopic signatures that reveal where Ceres' ingredients originated. Another path forward involves drilling or melting through the crust to explore the subsurface. This idea feels more ambitious, almost dreamlike, but it captures the imagination because so much of Ceres' story lies beneath its dusty skin. A drill could penetrate the upper layers of regolith and the icy crust below, revealing how materials transition from solid to slushy to potentially liquid states. Even a few meters of depth would show how salts, clays, and ice mix. Going deeper might lead to pockets of brine that still move slowly under pressure. A melting probe, a thermal device that sinks by gently heating the surrounding ice, could glide downward without the need for mechanical drilling, carrying sensors that listen to tiny cracks or measure chemical changes as it descends. Reaching the deeper layers of Ceres may help determine whether brine still circulates, whether heat remains trapped below, and how thick the crust truly is. a lander equipped with seismic instruments could listen for faint vibrations from shifting materials, helping to map the internal structure in extraordinary detail. Even if the interior is mostly silent, those quiet patterns would tell a story of density, layering, and subtle movement. Future missions also envision orbiters that build on Dawn's success but incorporate more advanced technology. Next-generation ion engines could glide through space with even greater efficiency, carrying heavier instruments or following more complex orbital paths. These orbiters could descend lower than Dawn ever could, passing within kilometers of the surface to detect fine-scale chemistry and temperature variations. Some concepts include radar instruments capable of probing beneath the crust, imaging hidden layers of ice and rock with remarkable clarity. Others propose ultraviolet or submillimeter sensors to detect faint gases that might escape from brine pockets. A future orbiter might even adopt a highly elliptical path, diving low over specific regions before soaring high again, allowing scientists to study localized features in exquisite detail. Each pass would refine maps, sharpen profiles, and reveal more about the hidden processes that shape the dwarf planet. Landers designed for Ceres would need to move differently than those on Mars or the Moon. In low gravity, a simple hop could send a lander drifting meters, or even tens of meters, across the surface. Engineers imagined small, agile probes that bounce gently between locations, using cold gas thrusters or mechanical springs to reposition themselves. These hopping landers could explore crater floors, climb the edges of ancient depressions, or approach bright mineral deposits without heavy wheels or tracks. They might carry small scoops to gather material, microscopes to study grain structure, or spectrometers to identify chemical signatures directly on the surface. Such landers could also deploy tiny sensors that nestle into cracks or soft soil, listening for temperature changes or shifts in mineral chemistry. Over time, these readings might reveal how frost forms and disappears, how salts absorb or release heat, or how the surface responds to the slow passage of Ceres' long seasons. Studying Ceres more deeply would also refine our ability to explore other icy worlds. The dwarf planet is a gentle proving ground for missions that will eventually travel to Europa, Enceladus, Titan, and distant Kuiper Belt bodies. Techniques developed for navigating low gravity, analyzing exotic chemistry, or detecting subsurface liquids would be applicable almost everywhere water and rock meet in cold environments. Ceres offers a nearby laboratory for perfecting such approaches before sending more ambitious missions to the far reaches of the solar system. Another future possibility involves long-lived monitoring stations placed on or near the surface. These instruments could track temperature cycles through Cererian days and years, observing how frost shifts, how salts brighten or fade, and whether small gas emissions ever escape from the interior. A small seismic network could listen for internal creaks, offering hints about warm pockets or slow movements of brine. Even a modest set of instruments left behind to quietly listen could provide insights no orbiter or brief landing could capture. There is also growing interest in understanding Ceres from a human exploration perspective. Although the dwarf planet is far too cold and too faintly lit to serve as a long-term settlement, its water resources could someday support robotic outposts or refueling stations. Extracting water from the crust could allow future spacecraft to generate fuel, extending missions deeper into the outer solar system. While this remains a distant possibility, Ceres' composition makes it an appealing candidate for such future endeavours. Looking ahead, the exploration of Ceres feels like turning the page of a book not yet finished. The chapters already uncovered reveal a world shaped by water, chemistry, and gentle internal processes, but many mysteries remain. How deep is the brine layer? How long did the ancient ocean last? What is the exact nature of the organic materials near a Nutet crater? How active is the interior today? Each of these questions invites new missions, new designs, and new approaches to understanding. Ceres waits patiently for these visitors. It awaits the precision of a sample return arm, the warmth of a melting probe, the quiet hum of next-generation ion engines, the soft hop of a lander exploring crater floors. It invites orbiters to drift close, instruments to listen, and scientists to imagine creative new ways to study its gentle mysteries. In the stillness of the asteroid belt, Ceres holds on to its secrets with quiet dignity. And one day, perhaps not too far in the future, new explorers will return to continue the story, uncovering details that deepen our understanding not only of this dwarf planet, but of how water, rock, and time shape the entire solar system. As you rise slowly away from the surface of Ceres, it becomes easier to see the gentle curves of the dwarf planet spreading out beneath you. At first, the horizon feels close, shaped by the smooth outlines of ancient craters and muted ridges. As the distance grows, those familiar features soften into patterns of light and shadow, until the entire landscape begins to blend into the round, quiet form of the world itself. The bright patches of Okator crater still glimmer faintly, even from far above, like tiny reflections catching the last traces of sunlight. Ahuna Mons appears as a pale rise, a solitary mountain whose icy slopes now blend into the surrounding plains. The longer you drift upward, the more these landmarks become gentle reminders of the unique character of this small world. Ceres begins to shrink, not abruptly but with steady calm, as though it is simply settling back into the space it has always known. Its charcoal grey surface fades into a smooth sphere, soft in colour and understated in brightness. The contrast between its dark plains and reflective salts becomes subtler, until only the general glow of its round shape remains. In this view, Ceres looks peaceful, suspended in the middle of an enormous expanse, where silence is the default, and time moves slowly enough to feel infinite. As the distance increases, the details of its geology return in memory. The scattered craters, each shaped by collisions that occurred over billions of years, the landslides that drifted across icy slopes, the bright mineral fans that mark places where brines once touched the surface, the fractures and troughs that hint at a restless past, when heat and water shaped the interior. All of these details were once hidden beneath its unassuming exterior, revealed only through the quiet persistence of exploration. Now drifting upward, these pieces form a tapestry of history that rests within the dwarf planet's rounded silhouette. The chemistry of Ceres also lingers in your thoughts as the world recedes. The hydrated minerals that carry the memory of water-rock interactions, the carbonates that shimmer like ancient frost, the ammonia-rich clays that whisper of a birthplace beyond the warmer regions near the sun, the organic compounds scattered in patches, hinting at processes that reach back to the earliest days of the solar system. These chemical stories remain on the surface even as they fade from view, locked within minerals that have survived vast eras of cold and silence. Soon, the dwarf planet no longer fills your vision. It becomes a sphere no larger than a pebble, floating in the asteroid belt like a lantern left burning in the distance. Its roundness, so different from the irregular shapes of nearby asteroids, marks it as something special, something shaped not only by collisions but by its own gravity and internal warmth. Even from afar, that distinction remains clear. Ceres is a quiet world, but not a simple one. It carries layers of ice, salt, rock, and history, each revealing a different piece of the story of how planets and dwarf planets came to be. As your point of view widens, the asteroid belt stretches outward in every direction. It does not appear as a dense field of tumbling rocks, as it is sometimes imagined, but as an enormous region of mostly empty space. Small worlds drift at great distances from one another, each following its orbit in patient solitude. Ceres moves among them like an anchor point, its size and roundness making it stand out even here. The belt looks calm from this perspective, a place where objects glide silently through the faint sunlight, influenced by nothing more dramatic than the slow pull of gravity. This quiet environment makes it easier to appreciate how delicately balanced Ceres is in its orbit. The dwarf planet circles the Sun every few Earth years, following the same path it has taken since the solar system's earliest days. Jupiter's gravitational influence shapes the space around it, but Ceres maintains its place, drifting in a zone where few disturbances reach it. The stillness of its surroundings amplifies its quiet beauty, making it feel like a world suspended in a long, unbroken moment. As you drift farther away, Ceres becomes smaller still, until it appears as a pale, round dot against the deep darkness of space. Its gentle glow recalls everything you have explored: the ancient ocean that once warmed its interior, the brines that still move beneath its crust, the bright spots that shimmer like tiny mirrors, the organic materials that hint at early chemistry, and the lone icy mountain that rose up from below. Each memory becomes a layer of its identity, enriching the tiny point of light that remains in sight. Letting your perspective widen even more, the sun comes into view, its warm light spreading thinly across the distant belt. From this vantage, Ceres looks almost fragile, a world so small that it seems miraculous it could hold such complexity within it. And yet it does. It holds evidence of water, heat, chemistry, and slow geological change. It holds the story of how small bodies can become surprisingly intricate, and it holds the quiet reminders that even the faintest glow can hide deep histories. Floating here, with Ceres now far behind, it becomes clear why such small worlds matter. They show that the solar system is not only shaped by giants like Jupiter or Earth, but also by modest spheres of ice and rock that preserve the ancient past. They help illuminate how planets formed, how water moved through the early disk, and how chemistry evolved in places far from the sun's warmth. They remind you that beauty in the solar system is not always grand or dramatic. Sometimes it is soft, understated, and revealed only through patient observation. The asteroid belt stretches like a calm sea around you now, each small world a note in a quiet cosmic chord. Ceres, though distant, is still part of that harmony. Its story is woven into the larger story of the solar system, and as you drift onward, you carry that sense of gentle wonder with you. The dwarf planet may be shrinking into the distance, but its presence remains in the mind's eye, a reminder that even the smallest worlds can inspire deep reflection. Allowing yourself to drift farther, you feel the transition toward the peaceful conclusion ahead. The journey with Ceres has been one of subtle colours, ancient ice, complex chemistry, and quiet surprises. Now, as the world becomes a soft speck behind you, the calmness of the asteroid belt becomes the final backdrop, inviting you to settle into a reflective mood. The dwarf planet fades, but the sense of stillness it embodies stays with you, guiding you gently toward the final thoughts that wait on the horizon. As the journey settles into a quiet stillness, it becomes easy to appreciate how Ceres represents a kind of beauty that does not demand attention, yet rewards it endlessly once noticed. So many worlds in the solar system announce themselves with drama: towering mountains, dense atmospheres, erupting plumes, sweeping storms. Ceres does none of that. It speaks softly, through faint mineral glows and muted colours, through gentle slopes, quiet chemistry, and a history written in layers rather than carved by violence. It is the sort of world that reveals itself slowly, asking you to pause, breathe, and look with patience. Reflecting on what Ceres holds within its small frame, you begin to see how subtly powerful a dwarf planet can be. Its bright spots alone carry a story that stretches from deep within the crust to the very surface, where briny water once rose and left behind shimmering salts. They are reminders that even in the cold, faint sunlight of the asteroid belt, movement once occurred. Water flowed, dissolved minerals, and carried them upward through fractures before releasing them into the airless quiet. These reflective patches are not grand in size, but they represent something profound, evidence that a small world, nearly forgotten in the shadows of larger planets, once pulsed with internal warmth. Beneath the surface lies an even larger story, one that began when Ceres was young and held a global ocean beneath its crust. Warmed by the gentle heat of radioactive decay, this ocean allowed rock and water to interact for long stretches of time. The minerals that formed during this period still rest across the surface: hydrated clays, carbonates, and ammonia-rich compounds that hint at origins far from the sun. These clues are gentle rather than bold, requiring careful study. Yet together they reveal a world that bridged the inner and outer solar system, blending ingredients from regions that would later give rise to entirely different kinds of planets. And woven through this deep history is the possibility, quiet, remote, but not entirely out of reach, that Ceres once held environments where life could have emerged. Not thriving ecosystems, not forests or oceans teeming with movement, but tiny, simple forms clinging to warmth and chemistry in dark pockets of brine. Nothing suggests such life existed, yet the ingredients are intriguing: water, organic molecules, chemical gradients, and the slow passage of time. In contemplating this possibility, Ceres becomes a gentle reminder that habitability can take many forms, and that even the smallest worlds may have briefly brushed against the conditions necessary for life to begin. Across the surface, the long history of impacts and landslides forms another quiet chapter. These features speak not of chaos, but of gradual shaping over billions of years. Craters soften with time, slopes slip slowly under gravity's patient pull, and frost gathers in shadowed pockets where sunlight never reaches. The dwarf planet's long orbit governs these patterns, setting the rhythm for sublimation, coulis, and the migration of ice. Everything happens slowly here, almost dreamlike, as though the entire world moves at a pace designed to calm the viewer rather than overwhelm. Stepping back to see the whole, the geology, chemistry, water history, and bright mineral trails come together as parts of one broader story. A story about how small worlds preserve the earliest chapters of the solar system. Ceres, in its silence, carries memories that the larger planets lost long ago. It preserves ancient temperature gradients, records the distribution of water during the first few million years, and keeps safe the delicate minerals that formed in environments long vanished from most other worlds. Through its chemistry alone, it links the icy realms beyond the giant planets to the rocky neighborhood nearer the sun, forming a bridge between extremes. There is something deeply comforting in this idea of quiet significance. It reminds you that meaning does not always come from scale or spectacle. Sometimes it comes from subtlety, from a world so calm and steady that it becomes a sanctuary for history. Ceres shows that small bodies matter just as much as the giants. They hold answers not because they change dramatically, but because they change just enough. They record the past without erasing it. They teach through gentleness rather than force. As you drift away from the dwarf planet and allow these thoughts to settle, a sense of gratitude naturally arises. Gratitude for the chance to explore such a soft-spoken world, and gratitude for the listener who has made this quiet journey worthwhile. Sharing a voyage through a place as understated as Ceres is a reminder that science can be peaceful, reflective, and calming, offering space to slow down and breathe even while learning something new. Thank you for taking the time to drift through this world, to let its subtle textures and ancient water stories unfold at their own pace. And now, with the dwarf planet resting far behind and the calm of the asteroid belt surrounding you, let the final thought settle gently. Even the smallest worlds can leave the deepest sense of wonder. Allow that stillness to follow you as the journey comes to an end, carrying you softly toward rest, like a quiet world drifting through starlight,